like all of them were kind of stopped. That was basically demo. Demos are created to help the users, right? But what was happening was it said like start from here, and they were clicking that and they thought the registration process was done, whereas they were just seeing like a video, right? It was embedded in the website, which was not working. Incorrect settings. We often forget the instructions which we are giving to the users. We say, okay, go to the settings and then make these changes. Now, what settings? Account settings? Is it the settings of your profile? Is it the setting of your YubiKey, etc. was not there. Instructions was not clear, and we also tested both the Yubico instructions as well as the Google instructions. Why Google? Because that's the first place we go when we want to learn something, right? Or any other search browser. And then there were some confusion points as well. So these were the points where people were stopped and they required the intervention of a researcher to help them, right? So that means that if it happens in your day-to-day activity, I will not be using the tool itself, right? So if I'm stopped, so they require that kind of intervention. Another thing which we noticed was there were some confusion points and the instructions was definitely not clear. So what do we mean by form factor? How many of us have tried to like insert a USB device and we cannot do it in the first attempt, right? Even now, I was trying and it was not, right? So for that, YubiKey actually changed that. They only have like, you can insert it either way, but it only works on one side. And that's the problem. So they were trying to insert and it was not blinking, nothing was there. So they were like, oh, the key does not work. That's what we do it in the first place, right? After like 5 minutes. And that was what's happening. Now, it might feel often at times when I give these talks to like more like kind of serious cybersecurity conferences, they are like, oh, this is social science. This is not really cybersecurity, right? But what happens if we are creating the tools people are not even using? That means they are trying for other ways which are not very secure. So that's how it gets related. So then later on in 2019, we repeated this study, but with older adults. By older adults, what I mean is like by definition, we had people who are 60 plus, and we wanted to understand that why, like whether we can motivate the older adults for this particular YubiKeys or not. YubiKeys or not. So what are older adults' risk perceptions of online identity and credential theft attacks? What are older adults' mitigation strategies? And do usage patterns and perceptions differ for older adults regarding MFA? So this study came from the fact that I am unofficial IT support from my parents, and I don't want that to happen for everyone. So we wanted to make sure that that works. So we had 10 participants through snowball sampling. As we know earlier, snowball sampling is when you try to like approach people and through them you kind of recruit other people and snowball and such that. So like a snowball, it grows. So have a personal laptop, have email or social media accounts, similar protocol were there. Now the time here is extremely important. On an average, they took 52 minutes, like about an hour to register, only to register, not even use it. How many of us will give an hour and then still try to use it? I won't be able to, right? And these were people who teach computer science, okay, who have been there, who have been the early adopters of internet and so on, and even they took about an hour. So what were the issues? Device and browser incompatibility. So now Yubico has created several keys which are compatible with several devices, several browsers as well. But initially they created, which was not very compatible, they were not really communicating why they need it and so on. Outdated instructions, right? We always know about legacy code issues. What happens when there are outdated instructions? People really cannot use it, and even we could not register. We had to actually tell them that you need to update your instructions, and then the study continued. Privacy and security trade-off, that is something which we all talk about in the user-centered security, that how they trade off so that to get into usability aspect. And risk and benefit communication is not there. Why do I need MFA? I don't have anything to protect, right? These are the people who have money. Okay, I was a student, I did not, so of course my account needs to be protected, but these are the people who are getting scammed through these aspects. And form factor was another issue, because a lot of the older adults were using Apple products, and the key which was compatible with it is even less than 1 penny, 1 cent, right? So people were losing it all the time, right? So even the key which they had used in the instant, they kind of lost it, and that was at that point of time more than about 50 bucks, right? 50 USDs. So that means they were losing it not due to any other issue. Another thing we are not noticing is the visual impairment. So these were people who had some visual impairment. For them to kind of notice, okay, where is the port and kind of use it, that was difficult as well. And fine motor skills, they were unable to even insert in some aspects because they were having some motor skill issues. So after learning all of this, I was like, now I have my own lab. Now I want to be a little bit more creative. So my future directions, and this is directly taken from my defense, I wanted to understand the risk profiles based on the strategy, and that's how I developed my final, and then do the usability, but also have diverse population and varied. And that's how the study came, evaluating the usability of multi-factor authentication security keys for athletes, right? Why athletes is something which I will be talking about. So these are my students who worked in this project. So before I start with that, I wanted to discuss about TBI, or traumatic brain injury. It is an injury that affects how the brain works. It is a major cause of death and disability in the United States. Anyone can experience a TBI, but data suggests that some groups are at greater risk for getting TBI or having worse health outcomes after the injury. And that happens a lot with athletes, right? Excuse me. Many wrestlers, they have, we call like in the ears, you can see that it's broken, it's kind of rejoined and all of that. That's also called the wrestler's ears. And all of that actually creates a TBI, which studies and CDC particularly has shown. However, little to no research evaluates secure authentication decision making for individuals with TBI or other transient or permanent cognitive impairments. Even with like usual studies, we only saw that 9.1% looked into it. So I found no studies which were looking into it, which as somebody who is trying to apply for grants was like, yay, there is something which I can be able to do. But I will be discussing about that in a minute, what happened. So thereafter, we are looking into blood biomarkers. Why blood biomarkers? Because it is a biological formula found in blood, other blood fluids or tissues that is a sign of a normal or abnormal process or of a condition or disease. A biomarker may be used to see how well the body responds to a treatment or disease. Now, the National Cancer Institute and other studies do not say that it directly shows TBI. However, blood biomarkers are currently under investigation and as potential predictors of TBI-related long-term brain health as well. So if you are not even self-reporting, and sometimes they are not diagnosed, this is a good indicator to understand what's going on. So again, so particularly we were, one potential promising biomarker is the brain-derived neurotrophic factor, which has been shown to have beneficial impacts, and that is something which we are going to analyze. Of course, you can ask that I am not a medical professional, but I am collaborating with people who actually work on this on day-to-day basis. And a blood biomarker is up to, if we want to go for like a good one, is up to $10,000. So that is why this is still something which I want to achieve. So importantly, BDNF, which I discussed, levels relate to cognitive performance. So we can actually show the correlation, if at all there is a correlation in these aspects. So what we proposed conducting multiple user studies of ubiquitosecurity key with individuals who have suffered mild or severe TBIs, not just by self-reporting, but actually there is a mechanism to know. But now see what's happening. Still under IRB approval after 2 years. Right? Why? We are taking blood from the people. So those who don't know, IRB are the ethical review boards, and they have several levels of aspects. One is exempt, which is usually how my studies go through. Easier one, you get exempt in a month or something, depending on the institution. Then there is expedited, and there is full board. So it's going through full board and all of the other details. Moreover, if I'm trying to apply for a grant, again, this is $10,000 for one particular machine, right? I need multiple of them. And if I try to do that, they need initial work, and there is no initial work which I can show. So I was like, okay, let me use my own funds which I have and do this pilot study, but then also there is some IRB requirements. So in this particular study, I have not done the TBI analysis, but that is something which is going on right now. So what we did, we had 10 participants through snowball sampling again, 5 athletes, 5 non-athletes, and 3 TBI diagnosed, right? So others can have, but it is not diagnosed. Again, the same thing. The phase 1 here, I changed a little bit. I actually asked about their password habits because that's how it is coming, right? So that you cannot memorize, and that's why we are going for passwordless. And the great thing is, yesterday we did talk about passwordless authentication, so that I don't have to explain. But we used Microsoft as well, and we discussed several issues with Microsoft, right? One of them is basically it is not passwordless if you are requiring to authenticate it with their own app, which is Authy in this case. Another problem with this passwordless authentication is if your organization is not allowing, for us it is not allowing, in that case you cannot usually have security keys. So we had to create like spam accounts in that case. So, and then we did a day-to-day longitudinal usage study for 3 months as well. So let's discuss about the time in the next slides. So first thing is weak password length as good as 1, 2, 3, 4. These are students, right? Literally somebody is still using 1, 2, 3, 4 as their password, even after all these years of password research, right? People are sharing passwords. That is like in between couples, if people have not gone through their phase, but sharing Facebook credentials with my partner to gain trust and all of that is still happening, but in different aspects. Easy to guess passwords like we learned about August 2018. That's definitely the team they play for, their favorite team, which is available easily. Dictionary attacks are pretty common. And they, apart from their university account, which really made it mandatory, they are not using 2FA for anything. And thanks to some people, like for example in Twitter, they are actually discouraging people to use 2FA with their recent changes. But anyways, I have my personal opinions about it. So what happened? We had 10 participants, the distribution was quite equal, and the time to completion you can take is anywhere between 21 minutes to about 9 minutes. Again, this is not ideal if you are trying to register in the first place. But what happened? Let's do a little bit more deep dive. Unable to find instructions. Participants are still unable to find instructions. And the most funny part is if you actually go to Yubico, there are no instructions. They have delegated it entirely to Google, but they have still the outdated instructions, but in a grayed out fashion, which we don't know why is that if they are delegating it anyways. Difficult to find the correct device, like there are multiple YubiKeys, so they don't, YubiKeys, so they don't know exactly what device I'm talking about, and the protocol changes accordingly, and also the security changes as well. Instructions are unavailable, easy installation with Google aspects, but again, it was difficult to find. First part is understanding of MFA. We are still kind of lagging why it is important, the risk communication, why do you need 2FA? Every conference I go to, the first thing which people say is we need two-factor authentication on everything, but still we are not communicating it outside of the security community in a way. Form factor, which I will be discussing, and there will be an interactive session between us. Inconvenient, 80% of the participants use MFA on their phone already. Why do I need a different device? If I have actually having problems, so what TBI does is does not do like long-term memory loss. It usually does short-term memory loss. So if I'm doing that, then I will not remember to take my keys everywhere, right? So I have my phone, but why am I using it? A physical, but they did say it is a physical object is more secure, but I have my phone. I will protect it more rather than a key which is lost in my purse or something. Lack of concern for security, not thought about in daily life. And this is not from the longitudinal study. This is just the initial registration process. So people really don't care so long as it's not convenient and everything. People are tied to their phones already. The extra physical security is nice, but it's not enough to make people switch from systems. I already have my phone on me and they are not happy about it. So then we did their longitudinal study for 3 months where they actually used this and they did the sign-in. And I wanted to show the screenshot of what it shows right now. And as we discussed, it is still it is making more difficult. So they don't have the option where you can sign in there, right? As we discussed, they have sign-in option. When you go to the sign-in option, then you have to sign in with a security key, right? And if the security key is lost or something, there is no way you can actually like forget password. There is nothing, no option such as that, right? So that is a concern. So every 2 weeks, we actually did a check-in, and this was done through Zoom. And so study highlights usability daily was much better than in comparison to the registration. So if we can actually motivate people to do it, people are actually liking just insert the key and using it. So varied results emphasize separate analysis for 2FA setup and so on. But now I have a couple of questions for the audience. So let's do. How many do you think in those 10 participants lost their keys?
Which keys?
The YubiKeys.
How?
Sorry, half? No, actually not half. 3 people lost, but the first person lost within 2 hours of the study. Okay, and this is like, it's an expensive key and they are seeing the utilization, but they lost it. Okay, how many shared their keys?
Oh, no.
5, half, all of them. All of them shared their keys because they were, again, these are students, they are living in a dorm, etc. You can add at least 35 accounts. They're like, why don't I share? My friend will also use. This is you inspired me to use this key, right? So now I want my friends to use it as well, but not buy, share it, right?
Where else did they use their keys though? I mean,
Oh yeah, so then they became very curious. So that's an interesting question. They went to the Yubico, they saw how you can add that. So they were using it for their personal accounts as well, the YubiKey, which you can add. We just gave the keys to them. We were not following up on that. So yeah, that was really very interesting. And the other people were also using. So this one key had multiple Gmail accounts added and personals.
so what do they like hang it outside the dorm room or something?
Exactly. So okay.
Same principle as sharing your Netflix account.
Yes, and I don't know how many of us we know, like the doorknob sock thingy, like so they were literally hanging out the keys in there and people were just using it. And this was very interesting to us because I have never seen this model even for other studies which we have done. They have shared, but not like that, but that's what they were doing. Yes, and to a point, one of the participants, like literally they forgot and they were like, they really needed the access to their Gmail. They asked somebody else, hey, so they also know the password, not that they just have the key. So they could log into their device and they had a call and they're like, oh, can you just use the key which is there, and they used it. So yes, so this is the mental model which we are kind of dealing with, even if we think that, yes, that's what the next steps. How many broke the keys? No, they actually did, 2 of them. And one of them, they were using a Windows machine and the key was broken inside, which we had like IT support and all of that to help. So just so you know, now Yubico actually gives you 24/7 support, which is not 24/7, but it does give you that support. So yes, they did break the keys as well. So now what I want to do is actually study how TBI related aspects can be kind of find the correlation. So we are kind of running the test, and that's what I will be doing this summer. And not just look into YubiKeys, but actually understanding that how we can build more secure technology, but for other population as well, and to look into older adults. Because as we were discussing in the yesterday that unfortunately older adults go through some diseases such as Alzheimer's as well. So for them to remember the passwords, it's not possible. I know we should not write password, that is something which I tell, but I have written passwords for my parents so that they can just refer back to that, because they will forget, I will forget, at least it is written somewhere and I have the copy of it as well if needed. So that is something which I want to study. So yes, I'm open to questions, and this is my contact details. Thank you.
I see a bright future for Fido here, absolutely. Questions? There must be questions.
Yeah.
Yes. Did you talk, when you were talking about password habits, did you also talk about biometrics, like fingerprints? Did they use it?
Yes. So that was very interesting, which we found out. Whenever we say that, are you using biometrics? They never, no, we are not using it. But everybody was using their fingerprint for their phone. So when we kind of probed into that, yes, that is biometric. Yes, that's just. So they don't even like, phone has been inbuilt into our system in such a way that when we were even using facial or something, we are not even recognizing that that is what we are. So that was very interesting too. Yeah.
Really fascinating one. I'm very curious if you have any recommendations for maybe like populations like older adults for how they can better manage their passwords. So password manager.
Yes. So the next talk I know is on password managers, and that is something which we also asked, at least older adults I'll come back, but to this population, and none of them were using password managers. The only thing they were using is the browser inbuilt. in a way password manager, right, to kind of remember it, but not any specific ones which are actually securing with like a master key or something, except like their device. And everybody was even sharing their device password, right? So for older adults, the another problem is, yes, password managers are helpful, they are secure or something, but then the thing is they have to learn every time we build another tool to it. And I'm not saying like, okay, 60 above means that person is old or something, but I'm also talking about people who are probably needing caregiving for their accounts and so on, right? So this is another concern which I am personally really looking into, like how this caregiving access control is also a concern. So if they are using this key, right, and they have lost it, even the caregiver cannot help. And there can be abusive caregivers too. So from the security perspective, definitely password managers is the way to go. Other things what we can do is, like for example, UBCO is working towards it. Now they have added the keys NFCs, right, which are contactless. So that is much easier rather than like breaking of the keys. That was one of the reasons they broke. So these are a couple of things which we can definitely do. Of course.
Okay, then I will say thank you again.
Thank you.
Do I need to push anything, or is the sound good?
Okay.
Good?
Yeah.
Wonderful. Password managers. I did the talk. That was nice. That is 3 years ago, 4 years ago, something like that. And I thought, you know what? I'll repeat this in a while. So much have changed. I did not foresee the whole corona thing, but that changed a lot. So yeah, I'm back, and I'm here to answer how hard can it be to choose a password manager. I just want to remind everybody, I wore this t-shirt yesterday, security at expense of usability comes at the expense of security. I think it's a nice way of saying usability and security is actually connected very closely. It's not opposite. You can treat it like opposites. It's not a good idea. You'll lose. They're very connected. So This is actually the cat picture from my previous presentation. I absolutely adore it. I think everybody should aspire to be this attentive when it comes to password managers. Yes. About me. First of all, I'm Cecilia. I work as a consultant with security and testing at a company called Bouvet. I have what's called a broad background. My bachelor degree is educational psychology, or pedagogics if you want, and my master is in what's called digital culture or philosophy of technology. And whenever I say this, people are like, that sounds interesting. Do you know anything like useful? And then I was like, I also have a year of nurse school, and they're like, okay, why? I was like, because I like people. I'm really interested in people. And what are they doing, all these people? Why are they doing what they're doing? I want to know. I want to understand this. I grew up online. I'm old, by the way, but I grew up online, which means that I've been through a lot of paradigm shifts from a situation where you couldn't really do anything online. You could talk to people and send text files, and if you were really, really dedicated, you could send really pixelated video clips. But today, it's something completely different. So we need to do other things today than when I grew up. I just want to make sure that everybody understands. I will be talking about password managers as in human-to-machine authentication, not machine-to-machine authentication. That's vaults, and I don't care about those. Whenever I say anything about password managers, people are like, okay, which one should I choose? And I want to do the consultant thing and say, well, it depends on what's got. No, it doesn't depend. As a private user, these are the only two criteria that matters. Does it cost anything? Do I know anyone who also uses this product? Those are the only two things ordinary private people care about. The reason your parents choose the one that you choose is not because you decided that's the best one, but because you chose it, you know it. Some are more resistant to cost than others, but yeah. In addition, if they're really interested in password managers, we have, oh, sorry about the contrast there. It was better on my screen than there. Sharing. A few really interested people like, okay, I'm not just going to think about cost, and if I know somebody that used the same product, they think about sharing. And there are only two teams. It's team I would love to be able to share my passwords, and I would absolutely do not want anyone to be able to see any of my passwords. Are you like, raise your hand if your team, it's nice to share passwords safely. Okay, sometimes. Yeah. Are you team, I will absolutely do not want to share any of my passwords. I want to make sure that nobody can access them at all times. And in, yeah, exactly. Like, is there anyone in between you? I heard it sometimes.
Like my wife and I share the password for our ISP account. So
Yeah.
she can pay the bills and I can do the technical thing.
Yeah, but you don't. So you share passwords safely. Yeah. For enterprises, this is a bit different. Enterprises consist of a broader variety of people, and they have a lot more concerns they need to solve. So for enterprises, what is considered user-friendly by me are all these things. Cost and familiarity still applies, sharing also, but the onboarding process is super important. Because how will you get your employees to use this? Well, if the onboarding process is terrible, it's going to cost you a lot of time to motivate them to go through that 92 minutes, 52 minutes process. So it has to be good. And then there's the offboarding process. A lot of companies, especially in Norway, they don't want to talk about offboarding. Offboarding is when an employee leaves willingly or unwillingly. Willingly is nice. That's good. That's not a problem. It's the unwillingly part that's difficult. But there's an unwilling part also. In addition, you need a recovery process. And this needs to be good. If the recovery process is bad, two things will happen. Your help desk will be overrun by requests. That's expensive. In addition, if the recovery process is bad, they will maybe start using the password manager once and never again. You'd think adding a password in the password manager in the right place is easy. I wish, really, I really wish that adding a password in the right place was given. It's not. Search. I'm old, so I know what an archive system looks like. There's a Princip, and I also know about Dewey. Young people do not know about Dewey. They Google everything. So if the search within the password manager is bad, whatever they can't find does not exist. Searching is super important. Platforms is no longer really a big question, but just make sure if you have like a weird platform, make sure that it's covered. And also, you need the password manager to be helpful in the right way. If it's too helpful, people get paranoid and uncomfortable. So like helpful, but not creepy. And the last thing that you need as a user-friendly criteria when you look into password managers are, can this password manager make good passwords? Again, I wish that was given, but it's not. So, yesterday we had a wonderful talk about universal design. And I so want us to be in the place now that I can say, you know what, these password managers are like 98% really good at universal design. And I looked into the criteria. We're not. Unfortunately, the only password managers, and I'm going to name them because they did this, that actually talks about it, even mention it, is 1Password. Everybody else, I suspect both Dashlane and LastPass, at least at some point, do some universal design testing. There are room for improvements, and some of the password managers have big room for improvements. But yeah, and it's really annoying because I wanted this to be a good tool for people who need this tool. But it's not. But okay. Enterprises also need collective billing, provisioning, all of this, safe sharing in teams, yeah, monitoring of quality, making sure that people and the training that you do is improving and working, and so on. Local language matters a lot. Espen mentioned yesterday the local language thing. Yes, local language matters. Do not expect all your employees to be fluent or comfortable in English or whatever language. Laws and regulations, audits are very common, especially for big companies and enterprises. And for European companies, the GDPR and Schrems 2 means that no American providers. For tech companies, Key Vault and APIs, which is machine-to-machine authentication, matters. This is tech company specific. A lot of companies don't need this feature at all. What has really changed the latest 3-4 years is the question about single sign-on. That was not a question 3-4 years ago. That was only like, okay, do you integrate with AD? And it's like, yeah, we do. Good. done. But now it's like, no, is it single sign-on? And I need to talk about the single sign-on part before I can tell you about password managers, good and bad, and do the scoring. Because the current terrain, or at least until a year ago, terrain was like this. By the way, these are not AI-generated drawings. These are artisan handmade by me. So yeah, this is my user. It could be me, it could be you. We need to log on to a machine, typically your PC at work. You use a password for that, and then you are logged in, and then you use a new password to log into your password manager, your master password. And then from your password manager, you find passwords to use on whatever application. Good. It's nice. It's very transparent. I know what's going on. Unfortunately, what is also going on is we kind of end up in a catch-22 problem, because I need to log on to my computer and my password manager to get the passwords to log on to my computer and my password manager. The password manager was supposed to solve this whole remembering the password problem. So what happens is you got shadow IT, here represented by a ghost. And then we got the devices. And the reason why we got shadow IT on the devices is because I have very little authority over my work computer, but my phone is mine. And it have all these really neat features. It has the function, like I can use my thumb, or I can use like the YubiKey if I'm really good, or a PIN, which is super easy to remember because it's only 4 digits. 6 if you're on iPhone, or just like, it's super easy. So, you know, and this works. The password manager makers have really strict rules for what kind of password you can have as your master password. That's okay. So you can have like really crappy passwords so you can get into the computer, and then have the really strong password if you want, or even have like this device on the side. But when the terrain now is changing to single sign-on, something else is going on. Now I have one password that I log on with. And depending on who I am as a user, the quality of that password is no longer under the control of the people who understand risk and the value of passwords. It's probably under my control. And I will probably follow some set of rules set by my company. But you can bet your money on that the password I want to make is an easy one, because I don't want to remember passwords. So I make a super easy password that now is not only giving me access to get into my device, it also opens my password vault and all my applications. In addition, we kind of didn't solve the problem with I need my password from my password manager to log on to my password manager. That problem is still there. So we still get the whole shadow IT problem. But with a single sign-on, you also get some added problems. You get added problem with who owns the device. Will single sign-on work on that device? If it works on that device, is that device secured well enough? I don't know. And in addition, what's going on here is really difficult for me as a user to understand, because it's magic. It just happens behind the scenes, and I have no influence over it. So you take away my ability to consider, is the right thing happening or not? I just have to trust that the right thing is happening. So no matter how much training you give me, it doesn't matter, because I can't really see this part now. In addition, single sign-on and magic, it's kind of uneasy. It gives me a lot of questions, like, can the company access my vault? Like my passwords? If they do, will I notice? And if they do, is this okay? If I'm a CEO or work in HR or accounting, is like every role okay with the single sign-on situation? How do I sign out? If I sign out, how do I sign in again? Like, is this easy? And a lot of the time, if the company really makes this so frictionless as absolutely possible, they will set up your single sign-on. They will set up your password manager for you. They will start filling your password manager with like company passwords that you should have access to. Awesome. Do I know that I have access to important things? Because if I don't know that I have access to important things, I will not protect those important things because I didn't know they were there. And then we have another problem. That is, okay, we have this very smooth situation, but that is only at work. And I'm pretty sure all of us have been working towards a goal that people have secure behavior, not just at work, but also at home. And companies should really care about the at-home part as well, because phishing and fraud does not only happen in company hours. And I think we should remember this example. Even the makers of password managers experience breaches out of company hours. This was the LastPass incident that happened at an employee's home computer. So you cannot, while private passwords are private, the risk is still global, both at home and within company hours. So, do you understand? Single sign-on changes the terrain and the usability and the user experience a lot. And you have to have that in mind when you're choosing a password manager. Yes. You following me so far? Please note if, yeah, good. So, oh yeah, oh hang on, let me fix that. Yeah, that's what it's like. Like, I know not everybody is like super enthusiastic about choosing password managers. I am. Everybody else just want to know the answer. So I'm not giving you the answer quite yet. You have to stick with me like a few more minutes. Onboarding. I want to show you a few examples on onboarding that really like, what? You know, bad ones, of course, the good ones. I don't want to show you the good ones. I want to show you the bad ones. As I said, onboarding, tone of voice, and the situation. This is Nordpass. They are new. And this situation, I absolutely loathed this. Like, this was terrible. I went through the registration process and everything, and I got this far, it's like, what? What is going on? I thought I like already made my master password. It took me a while to realize, no, I did not make a master password. I made an account at their website and within their system. I was like, why? Why am I now a customer? I just wanted to use the product. I didn't want to have like an active relationship. So it was confusing. In addition, they made a trap, and I hate this trap. And this trap is, make a password, and you start making a password, and then you push continue, and then it's like, you failed. And that is a trap. Do not make traps. Make sure that when I make that password, I understand all the rules so I can actually succeed at this. Software is a lot of tiny surfaces. Make sure that all the tiny surfaces are good and understandable. This is Keeper. I have two choices here. And I know request admin approval is not a good choice. My help desk people and the admin of the password manager will not thank me for pushing that button. So the only button I should push is send keeper push, but I don't know what that send keeper push do. Push what? To where? What will happen? I have no idea. I pushed it several times. I couldn't see anything happening. What is going on? Like, it has to be helpful, actually. And I don't have a copy of it here, but the email when you're onboarding people, make sure it's nice. Because a few of the emails are extremely techy in voice. Like, it's okay if you're onboarding only DevOps. If you're onboarding other humans, make sure it's nice and friendly and comforting. Shout out to Dashlane and OnePassword for actually having nice onboarding emails. And then was the add the password part. I thought I had a password manager, and now I can add records and folders and share folders. It's like, records? For what? And I realized it's whatever I'm doing, I'm not adding a folder or shared folder. So I click the record, and it's like, oh, now I got options. Why? Why can't I have the options to begin with? Why is there a record situation? I don't know. The language is difficult to understand. It's very domain specific. And as an ordinary user, it's hard. It's already hard to understand passwords and passphrases and vaults. Don't make it harder. But okay, I want passwords. I want useful passwords that are better than the password that I can make up. Okay, I guess the dice is kind of fun. I'm not sure what the cursing option means. But okay, I'm from the up north. Cursing is a part of my culture. I accept that. And this interface is like, I was starting to make a password and it's like, oh, what did I do wrong? I need to add a website to use it. I don't know. I did something wrong. I don't know what the wrong I did was. But now I'm not sure what is going on. Like, when I've done this, will it fail me? I don't know.
Is it plus?
These are actually pretty decent. These are far better than the previous ones. But making a good password is difficult. You'll have to deal with me for another few minutes, sorry. But these are showing more useful interfaces because some sites require this and some sites require that. And if it's a password that I am actually going to end up typing, can we make it into words that I can read? Never mind. Expert, short, Premier, LaTeX, or LaTeX, depending on what's your preference. I can read that because I can speak English, but it would be even nicer if it was in my local language. So yeah. Everybody cares about the price. Now, keychain is mentioned because you should not ignore what the user already have. Like, just allow it. Be nice. And perhaps in the future, they will see the benefit of choosing the option the company offers in addition. But, you know, respect that. In addition, KeyPass, that's your benchmark. When you're considering what am I paying for, use KeyPass. Here we are. This is the whole shebang. What should I choose? Well, it depends on where your tough spots are. Simple as that. This is my consideration. You are, of course, open to do your own. You can use the list of requirements that I have. But if you only want the answer, this is the answer. There you go. If you want to know why all of this, I would like to remind you that I am a consultant that also drink beers. So yes, thank you. I'll take questions first and comments in the break.
So first, a comment, especially.
Nice one. Okay, go. Go.
I mean, I have a comment and a question.
Sure.
Let's say the question. So I don't know how, but maybe it's a question for everyone for your next talk or somebody else's talk. But you mentioned about how many organizations or people think about onboarding and not offboarding. And I find it such a missed opportunity for single sign-on to not have even mentioned off as well, like single sign-on and off. Because now you have this SSO being deployed pervasively everywhere, and then it's so easy that you have an employee logging into more and more cloud services, then one day maybe you have to terminate them or they leave, and no one knows how do you log them out, apart from the main windows, and that's it.
Yeah, offboarding is a big deal, both from the other platforms, but if you decide that, well, okay, this person is, we have decided this person should leave and just pull the plug, you end up with a very uncomfortable situation, and that is that person may now not be able to access password they should be able to access, and they will probably make it known in the organization, and that will pull the rug underneath all efforts that you put into making people trust this process. So when I leave, willingly or unwillingly, I will no longer have my passwords. I'm not sure if I want to do that. I will now have a predictable system and reuse passwords in my private sphere and only have work passwords in the password vault, the ones that you can keep. That is not a good situation to be in. Make sure the offboarding is good. Yes?
And on the previous slide, the one with the what feature is where, there's first column, for example, some of them are good, some of them are okay. Which one is better?
Thank you for the, I didn't realize that is a cultural interpretation. Good is good. Okay is like, fine, whatever. Like, it's possible. But good makes me feel good.
And also in this table, do you know which one of them works with the offboarding correctly? Is there any one which does correct offboarding? So for example, if I leave the company, I still have my private ones?
All the one that says yes has good offboarding. Yeah.
Line.
Yeah.
Why not pass is not great if it gets most of the points?
Sorry, again?
Not pass. It says not great, but then it gets yes and most of the points are okay, which is, so why not great? How did you calculate? It's
I have not made a summary.
sorry,
Yeah.
it's onboarding.
It's the onboarding process. Yeah.
Maybe you should add a summary because you...
Maybe. But again, if you decide to go with North for whatever reason, make sure that you adapt the onboarding process. Like you can do, take action to improve the points. Yeah. More questions?
Yeah, so you gave a talk a few years ago. What are the 3 most interesting changes?
That is a very good question. I'm very happy you asked that because Bitwarden is one of the most interesting changes to this. Because Bitwarden, a few years ago, they were like at the same level as KeePass really, but they have really pulled a, an effort into this now. So yeah, that is one of the most interesting. The other most interesting thing that happened is that there's so many newcomers to the market now that just wasn't there before. Nor is new. Soho, probably not new, but more visible. Yeah, and then the LastPass has like a really uncomfortable incident. They already were problematic 3 years ago with the recovery process, but then they had the incident which makes it even harder to choose them. So yeah, but Bitwarden, good job.
Last one.
So what do you mean with the asterisk on last part of work private law?
Sorry, the asterisk with work private. The asterisk is referring to the incident. Yeah, it's something about you call it eat the same food that you make or something. There's a proverb for this. Dog fooding was it? Yeah. It's hard to trust a company that doesn't do the thing that they are selling you. Yes.
Do you want to see passwordless password manager?
I am very interested in how passwordless password managers, but I think the terrain will be.
I can spend 5 minutes later today to show you.
Yeah. Yeah.
Passwordless password manager. That's interesting.
Yeah.
Okay, I'm calling it a break there. Break for 21 minutes before Dario will go on stage. There's more sugar, of course, but there's also fruit out there in the hallway. Maybe that will help on today too. Yeah. Thank you. And we have with us Dario from Italy, studying in Italy. When I received this submission from you, I was like, oh, that
for introduction, because yeah, the title of the talk is quite good. I promise that we eventually make it probably. And so let's start by covering my back. The project has been developed with applicability in mind, but is quite academic oriented. We are going to talk about exotic machine learning models, and also about differential privacy. And if you want details on everything, there is the paper on arXiv, and you can check it out. Yes, our journey starts here. This is the rabbit hole, and we are ready to go in. We start with a background. Yeah, probably you already know these things, but it's just to be sure that everyone use the same names for the same things. So we are going to talk about password models. A password model is nothing more than a function that maps the password space, the key space, the set of possible passwords, to the set of natural numbers. More precisely, what it does is take all the passwords and gives an ordering to it. And if the password is on top, it means that the password is weak. If the password is at the end, it means that the password is strong. And the rank of that password in this ordering is called the guess number. So how many guesses an attacker gonna take in order to guess that password. Password models are everywhere in password security, and those are the things that we use to understand the security of passwords. Every password guessing attack, also dictionary attack, is a password model. So you can use a password model to generate guesses and perform guessing attacks. You can use a password model for password strength estimation to create password meters. And then you can do whatever you want. Distribution-aware hash functions and encryption, everything is based on password models. Now, for the sake of the talk, I'm going to focus on password strength meters, but everything I'm going to say more or less apply on all the other fields. So a password model is a data-driven approach, meaning that we have a setup phase, an inference phase. In the setup phase, we teach to the model the meaning of weak passwords. And we do this by using a set of passwords, a sample from a password distribution that in 99% of the cases is just a leak of public passwords that we found on the internet. And we use these parameters, this data to find the right parameters for the model. That is usually a machine learning model, usually. Now, when the model is ready, we can apply it for our purposes. And the cool thing is that the password model should give you a meaningful stress estimation also for passwords that are not in the training data by interpolating on the data that the model observed during the training. But here there is some main problem, and the main problem is always the same. Different people choose different passwords. And a password model can fit just a password distribution at a time. That means that if we have a password model that has been trained on American passwords, and we try to estimate the strength of a French password, even if the password is trivial for a French person, the model is going to tell us that that password is quite strong. Another message here is that a password model, if you train a password model on a certain data distribution, that password model is going to be optimal only for the data distribution. This is a very simple example. So we have two password models, one trained on Hungarian password and one trained on Polish passwords. And then we apply these password models in a guessing attack against a Hungarian leak and a Polish leak. As you can see, of course, the password model trained on the Hungarian password performs better. So the X is the number of guesses, while the Y is the percentage of guessed passwords. Instead, in the Polish setting, the Polish performs better compared to the Hungarian. Now, I have a question for you. We have a third password model, and this password model has been trained on the combination of the Polish and Hungarian leaks that we use to train the other two models. Can you forecast the behavior of this model? Is going to be better?
It's going to be in the middle of the two.
Yeah. Even if we train this model with twice the amount of password of their two, this model cannot beat the model that has been trained for that specific password distribution, but performs well in average in both the cases. That sucks. It means that regardless the amount of data we have to train a password model, there is no such a thing as a universal password model. So a model that once you train it, you can apply on every password distribution, obtain meaningful password stress estimation. That means that if you have a system and you want to create a password model for the system and you want to have meaningful estimates, you have to train a password model for that specific distribution. The main problem is that training a password model is not an easy thing to do. This is Bob. This Bob is going to be our example for the rest of the talk. So Bob is Italian. He has mustaches. Bob is a system administrator of Pizza.it. Bob wants to deploy a password stack meter for his users. But Bob is wise. Bob knows that he needs a tailored password stack meter for a password distribution of his users. So what Bob does is go on Google, is looking for the state-of-the-art password model. He finds the code on GitHub, and now he needs to fit the model. So train the model in order to represent the password distribution of his users. This is complicated because the only thing that Bob has is a set of hashes. He has not access to plain text passwords. Otherwise, Bob would have other problems. And so the only thing that Bob can do is go somewhere on Google looking for leaks and find a public leak that has a similar distribution to pizza.it. And this can be quite difficult. Even if Bob has the data, now he has to parse the leak, set up choose some hyperparameters, because usually those are the machine learning models, and you need to pick hyperparameters based on what you want to do, and then run the code. And training the model can take days of GPU time. Again, Bob is a simple person. Bob doesn't know anything about password leaks. Bob doesn't know anything about machine learning. His reaction is, I'm Italian, I can joke with it. So what Bob does is find the first plug and play of the shelf password model you can find on Google that has been probably training on RockU. And if you try to put Italian password, I guess, it gives you the wrong string destination. Now, the point of the project and the talk is understand if Bob, regardless the lack of resources and expertise of Bob, can he do better than that? The answer is yes, otherwise I will not be here. And actually, the real answer has been always under our nose, but we are getting there. So how to solve Bob's problem? Simple. We create a universal password model. It's trivial, no? A universal password model is a password model that can capture every password distribution simultaneously. That means that you train it once, and it can switch to the right guessing strategy based on the context. And it looks something like this. So we have the same password model. We apply it on Italian system. It produces Italian passwords first. We apply it on a Japanese website. It produces Japanese passwords first, and so on. And the model is the same. Now, I told you that a universal password model can decide the right guessing strategy based on the context, but the problem is, what I told you before, is that Bob has no access to plain text passwords. Bob does not know how his users' passwords look like. So the problem is how to define the context that the model can exploit in order to adapt. But we know that password and users' auxiliary information are correlated. And so if you are smart enough, you can exploit this correlation in order to understand the context. So given the auxiliary information, predict the underlying password distribution. So transmuting email addresses in password models. No? OK. And this brings us to the main character of the story, the universal neural cracking machine. It's just a cool name. Actually, I never use it to crack passwords. So yeah, it's just a password meter. But UNCM is a deep neural network composed by two components. The first component is called the configuration encoder, and then we have the real password model that is actually a conditional password model. And the idea is that the configuration encoder takes as inputs auxiliary information about the users of the system, of the target system, that in our implementation are just email addresses, and transform this information in something that we call the configuration seed. The configuration seed is just a vector. And this vector goes inside the password model. Now, the intuition is that this vector here represents a prior on the distribution of the unknown passwords that are associated to the users here. And the idea is that when we provide this configuration seed to the password model understands the context. So we are attacking these people here, and so on. It switches to the right guessing strategy. In actuality, the UNCM looks something like this, and now we are gonna cover a component at a time. So this is the configuration encoder. The configuration encoder is composed by two components. The first is the sub-encoder, and then there is the mixing encoder. So the idea is that the mixing encoder is the neural network. Actually, it's an aggregation of neural networks, but you can see it like a single model. And its task is to take a single email address and map it in a vector, in a format that can be understood by the mixing encoder that follows in the pipeline. We do this by breaking the email address in different components. Every component is parsed by a different neural network, and then we combine back these vectors, and we get a bigger vector at the end. I said that in implementation, we only use email addresses, but this approach can be extended to everything. If you have the data, for instance, if you have the username of the guy, you can create an additional module here and the result to the vector and get a better representation of the users in the system. This is the main part, the mixing encoder. And essentially what we do here is taking all the email addresses. For each email address, we apply a replica of the sub-encoder, and we get n vectors, where n is the number of email addresses. And the task of the mixing encoder is taking all this information and mixing it together and producing a single vector, the configuration seed. Now, it's not a simple aggregation. Also, this aggregation is a neural network. This is an attachment mechanism. We are going to talk about that later in the second part of the talk. But essentially, just to make you understand, is essentially the big building block used to build models such as GPT and such. It's the building block of transformers architecture. Now we have the configuration encoder that is the output of the configuration seed that is the output of the configuration encoder, and now it's the part of the password model. So as password model, we use state-of-the-art password model. It's a probabilistic password model, meaning that it's a neural network that maps each password to a probability. And it's an autoregressive character level machine learning model, meaning that given the radix of the password, we train the model to predict the next character. And you can use this model to generate passwords, assign probability, and everything you need from a password model. Now, we modified the original model. Indeed, this is a conditional password model. And the only thing you need to understand here is essentially we adapt the model in order to receive additional input, that is the configuration seed. And the idea is that with this configuration seed, we are able to change the behavior of this neural network without retaining it. So without changing the parameter of the network, based on this input, we can manipulate as we want the output of this neural network. Now, how do we train this thing? As training set, we use the leaks collection, the leak collection seed 0 day. It's a collection of more than 20,000 leaked web applications. Actually, it was quite dirty. We saved about 11,000, but still a lot of leaks. And essentially in the format email address and plaintext password. And it's composed by many small leaks. This is the distribution. And it also covers a quite broad geographic zone. So this is the top 25 top domains in the leak. So we have German, Korean, everything inside. Now, one thing that we understand is that usually a password model is trained at password level. It means that each iteration of training, what we do is sampling a password from the training set of a batch of non-correlated passwords and use it to change the parameters of the model. Now, IUCM does something different. Instead of using password level training, we do leak level training, meaning that each iteration we use our whole leak as training instance. And the training process looks something like this. So we have a collection of leaks. At each iteration, we sample a leak. Again, we have email addresses and plaintext passwords. We take the emails, we put it in the configuration encoder that produces the configuration seed that goes inside the password model. And then we take the plaintext passwords and we train the password model to predict these passwords, meaning to assign high probability to those passwords. In this process, the encoder and the password model are jointly trained as a single neural network, meaning that we are forcing the encoder to retrieve information from the email addresses, condense them in the seed, and training at the same moment the model in order to exploit the information that the encoder has recovered. At the next round, we do the same thing. We take another leak. We challenge the encoder with new information. We generate a new seed, and the password model is trained to guess those passwords. Does it work? Yes. Now, with this technique, we take an Italian website. We give all the information to the configuration encoder. This produces a seed, and the seed goes in the password model, and the password model generates passwords based on the context. Those are this is actually the output of the model. This is performance on guessing attacks. So those results are obtained averaging about 100 leaks. So those are the average of 100 guessing attacks on different 100 leaks. The green line is the UNCM, while the black line is the baseline. The baseline essentially is the same model, so the same password model we use for the UNCM, but it's trained in the standard way, meaning that we take all the leaks in the SIT0 day, we combine them together, and we use it to train the model. And one important thing to understand is that essentially this model and the UNCM are equivalent in the sense that they have been trained on the same data set. The only main difference is that UCM can also access the email addresses. And the architecture of the password model is the same. The neural networks have the same parameters, the same number of parameters. As you can see, the UNCM performs better. This is a little bit clearer in the plot on my left. And this is the ratio between the password guessed by the UNCM and the password guessed by the baseline. And I can see for initial guesses, the UNCM guesses about 3.5 times more passwords. And those are the weak passwords. Because when you have a password meter, the only thing you care is about guessing the weak passwords. So this is an example of what the baseline model is missing. So those are different websites. And the first line is the guess number assigned to these passwords from the baseline, while the second is the UNCM. And if we are going back to the previous example, while the baseline assign a quite high guess number to a trivial password, because the UNCM can adapt to the password distribution, assign a much more realistic guess number. However, for me, the cool part about this model is that it can perform at the same level, if not better, than password model that has been tailored for that specific password distribution. Here we have 3 examples. So we are attacking only Korean passwords, only Polish passwords, and only Taiwanese passwords. In the paper, we have more examples. Now, the green line is the UNCM, the black line is the baseline, what we have seen before, while the red one is is a tailored model for that distribution, meaning that we train a model, a positive for that distribution. So we start from seed 0 day, we filter all the Korean leaks, and we train the model only on those leaks. And as you can see, even if that model has been carefully trained for the distribution on which we are testing the models, the UNCM is able to get the same results, plus it achieves better results at the end of the attack. And this gap gets wider as the Taylor training set shrinks, meaning that if you have no data to train the Taylor password model, the advantage you get using the universal real-time machine will be always greater. Now we are back to Bob. We have a solution for Bob now, because the only thing that Bob needs to do is download the pre-trained configuration encoder and password model. These are already trained. He gets the email addresses. It uses them as input for the configuration encoder. He gets the seed and combine the seed with the password model. And now the only thing he needs to do is send the password model plus the seed to the client side as password meter. So essentially what Bob did is create a tailored password model for his system without training and without data collection. Again, without any kind of expertise, Bob has been able to achieve a state-of-the-art result. However, it's not so easy. There is something that's lurking behind Bob. So there is a problem here, and the problem is that this seed here is a function of this information here. And this information is private, right? I mean, there are information from the user of the system. And even if the configuration seed is a stream compressed version of information here, we may have an attacker that accessing the seed can tell information about the users, and we don't want that. And so we have developed something that we call private UNCM. Sorry about that. I need to talk about differential privacy, but I'll be gentle. So let's assume we have a magic blender, okay? This magic blender has this property. You have a batch of apple, pears, and bananas, and in other universe, you have just pears and bananas. Now, the property of this blender is that if you use those two inputs, you get two smoothies that are indistinguishable. In the sense, if you taste this smoothie here, you cannot tell that the apple is not there. Now, in computer science, we don't call it magic anymore. We call it differential privacy. And we say that a blender is epsilon differentially private if, again, if you have two smoothies that differ from a single fruit, you cannot tell that fruit is missing. Now, maybe it's hard to follow, but this property implies that and for a small enough epsilon, if someone tastes your smoothie, this someone cannot tell any of the individual ingredients in the smoothie. And this is what we want for our seed. So forget about fruits, put email addresses. What we need is a blender that takes as input email addresses and produce two configuration seeds for which an attacker cannot tell which of the email addresses has been used to compute the seed. Actually, it was quite easy. Yeah. So in our setting, the blender is the mixing encoder, because those vectors are the output of the are a function of the email addresses. So the only thing we care is about this mixing encoder, and actually making the mixing encoder differentially private is quite easy. This is what normal attention mechanism looks like. The only thing we need to do is, apply a few tweaks. So we need to clip the output. So the first thing we need to do is, let me start again. In attention mechanism, we have two parts. The first part is the one that computes the attention scores. And those scores are the scores that we assign to each input, and we compute a certain kind of weighted average. And these weights are a function of two things: a query vector, that in our case is not really important, and the values vectors, where each value is an email address. And this part here is assumed to give an important score to each email address. Now we apply these weights to a projection of the values. So again, those are email addresses. We project them using another neural network, and then we apply the weights. And then we perform the sum, so getting a weighted average. Now, the problem with that is that if you want to achieve differential privacy, you need to do two things, mainly. The one is clip the value of inputs in order to impose a certain sensitivity, and then apply some kind of noise. Now, what we need to do here is compute the weights, but instead of using a softmax function, as before, we need to use a sigmoid function in order to remove any correlation between the inputs and then get the weights. Once we have the weights, those are not correlated, so we can apply these weights to the output of the neural network and then apply a clipping function, so constrain the L2 norm of these vectors. Once we have these vectors, we can sum them and then add some kind of noise. This noise is proportional to the sensitivity that we chose with the clipping function, and another other parameter z that defines the amount of noise we are gonna put. And of course, more noise you put, more privacy you get. Those are the results. So of course, if you use differential privacy, you are gonna lose utility, because what we are doing essentially is destroying information. So the green line is the UNCM, while the blue line is the private version, the one with the private configuration seeds. And as you can see, there is a utility loss, but it's quite limited. And still, we have an improvement over the baseline. Now, talking about privacy, is a little bit complicated, but the idea is that the level of privacy we get in this setting is a function of the size of the database. So that means the more user we have, the higher level of privacy we get. And on average, on our test set, we get about 0.7 epsilon. That is quite good, because essentially any value below 1.1 of epsilon it provides quite strong privacy guarantees. This is cool because it means that we can extend this framework to work on more and more sensitive data, if we want, this without threatening user privacy. So if we have more data, we can just add additional modules to parse this data and get better representation of the users, and so probably get better prior over the password distribution. So what we have learned, you can create universal password models. It's a little bit complicated, but the idea is just that you have a password model that it can adapt to the context, and then it's on you how to define the context. Another thing is that this is the proof that you can use user auxiliary information in an automated way to predict the underlying password distribution, and you can make this whole process private if you want. So we are going to make the models public. They are not public yet. But the idea is that we are going to pre-train these models, make them public so everyone can download it and make all the bobs out there happy. Personal announcement, I'm in the job market. If you are interested, just check my page. And I'm ready for questions.
And that's not a phishing test.
Hmm?
That's not a phishing test, the QR code. Standard joke. Any questions for Dario? Come on. Jim.
So actually, if you could turn back to the prior slide as well, I wanted to get the that URL as well. But my question is, you focused on the country that the email address belongs to, but I would also expect that men and women would have different password patterns. So would Bob at pizza.it and Alice at pizza.it have different sorts of common password distributions?
Absolutely, yes. But the problem is that we didn't have the right training set to learn that relation. But in case we will have more data, the model will have learned automatically that relation, exploit it to create better representation of that distribution. But in the paper, we are also results for different segmentation of the population. For instance, we are considering just e-commerce websites or other semantic groups. And the results are almost the same.
You were showing at one point comparisons between UNCM tailored models, which I understood in baseline. What is baseline in your case? What did you compare the baseline to? It was early, I think.
So, the question is, what's the baseline?
So
okay.
when you compared the tailored model, I understand you compared to a password model trained on region-specific data, like Japan or Italy or France. What is the baseline model?
Yeah, as I said, baseline model is, we can see it like an approximation of the universal password distribution, in the sense you get all the distributions you have, you put them together, and then you train the model to try to approximate that distribution.
So it's all the passwords put together and
yeah, ideally, yeah. This is the best model that you can have if you don't want to have a tailored model.
And the subsequent question, how does it perform against new TLDs? 3 days ago or 5 days ago, there's a .dad, so for all the fathers, they can get their own .dad domain name. How does it perform against unknown parts?
What do you mean?
So, for example, Octav at opaski.dad.
They're all men, so you get the male-female distribution in English, right?
We need a mom. I think the mom is already.
Yeah, but yeah, if the email address is not informative.
The default state of the model when it doesn't understand parts of.
Yeah, that's a good question. I don't have the plot here, but essentially when the model cannot extract information from the email addresses, it behaves like the baseline model. So essentially the curves are the same.
So regarding the input you gave from user data, like is there like a minimum of data you have to put in to like get kind of good results out of it?
Actually,
for example, if you create a new web page, at the end you don't have users at the beginning, right? So at which point can you benefit from the users to
Yeah, we didn't test that, but the password distribution is quite, so there are many small leaks in order of 100, and the model seems to perform well, but if we want results, I don't have anything to show you. But the idea is that the configuration seed can be updated. So you create the first one, and then maybe when you have the users, you perform the processing step, you get a new seed, and you get a new password model. And you can also adapt it, I mean, for no reason. Like if you add new users, you can just sample another seed and get fresh seeds and better models in theory.
Okay, so for example, if users do not want to state their real identity and their real email addresses, and they enter fake details, then how would this model perform or get biased by that?
Good question. Yeah, I don't know. In the sense, actually, I was thinking about an attack where an attacker could generate fake email addresses in order to bias the meter, in order to do something. But yes, if you're performing a kind of poisoning attack against the meter, yeah, we don't have a defense for that right now, also because it's not in our threat model.
And the easy answer, Dario, is that's against the terms and conditions, so you can't do that. More questions?
Can you go back to the slide where you compare the baseline performance with the new model?
Sorry, animations.
Yeah,
Almost there.
right. So, so if I understand correctly, like you have a password cracking dictionary that you would normally launch, and what you're doing with the model is that you like reorder this set. So the order of how you're gonna try and what you're gonna try is going to change based on the model. So my first question is like, what kind of base cracking dictionary do you use, or you like kind of recreate it completely?
Yeah, so you can do that. You can take a dictionary, apply the model, and reordering it. Yeah. But in this case, those are generated passwords. So use the password model as generative model. Mm-hmm. And essentially what you do is a beam search, and you generate all the passwords according to the probability that the model assigns. So there is no dictionary.
But this model then can be also used for this purpose, that if I have a dictionary, I want to rank the passwords, like how do I try for a specific attack, if I'm attacking a certain user or a different user?
Yeah, you can do it.
How,
Yeah. I'm gonna call it an end there, and we'll do 16, 17 minutes break. So thank you again, Dario. Now you're actually live on the internet as well.
All right.
Stefan.
Hello, internet.
Hello, internet.
All right. Almost good, right?
Okay. So we have Stefan from Sweden, from Trusec. Everlasting topic as well. How do people create passwords? And Stefan is sort of on the opposite end, how to understand how people think so we can crack their passwords. Hit it.
All right. Thank you very much for having me here. It's my first time at PasswordsCon. I've looked at a lot of videos. And I think it's going to be fun. I'm going to talk a little bit about password culture and how I have used this in my work to improve dictionary attacks. So first of all, I'm just going to make a disclaimer. This is a fixed point in time, right? What we're going to talk about now is like now and happening in this time. So 10 years from now, if you go back at this recording, if you can ever find it in 10 years, maybe my findings or my statements will not hold. We will see. Hopefully not, right? If people will have much better passwordless biometric brain scans or something to log in. About me, my name is Dr. Stefan Arvidsson. I work as a, I think it says on my card, it says like security software specialists. It's kind of like a very general term for being a specialist. I work at Trusec and I work at the Malmö office in Sweden. I do have an academic background, but it's in a totally different field. So I have a fancy thesis. You can find it somewhere and you can read it. And you can ask questions, like send me emails or questions about that later on if you want to. Also, I'm almost wearing the same thing I see here, but the suit is, guess it's my talk suit or outfit. So a little bit about TrueSec, because they were very gracious enough to send me here. We are a company that do cybersecurity on like a broad scale. We have a headquarters in Stockholm, and then we have satellite offices in most Scandinavian countries, except Norway, but we're looking at that at the moment. I like Norway, so why not? We also have people in US, some in South Korea, Germany, and so on. For me, though, TrueSec is a collection of exceptional experts. So this is why I think I've worked at TrueSec for 10 years now, and it's like I have these exceptional experts around me that I can ask for help, and we can collaborate, and I learn something new every day. So that is a little bit about TrueSec. Not the full sales pitch. I'm going to set the stage too a little bit. So I stumbled into this password field a little bit by chance. Of course, I've done passwords a lot privately, but for the recovery of passwords and how people think about passwords, it was actually a colleague of mine who started out with this, who like convinced my boss at the time to buy a gaming computer and put it under his desk. It was very warm when he was doing stuff. And then he decided to leave for another job, and the machine sort of like fell onto me. So there I had a Linux machine with an, I think it was an ATI card, and I had a lot of troubles with drivers, but it was running Hashcat. So, and then after I've been looking at a lot of passwords, I saw patterns emerge. And then I became interested in these patterns, and maybe like my academic background triggered, maybe I could figure out things, maybe I can use these patterns to improve the attacks, or like the recovery, password recovery. I guess also intertwined, we talked about that yesterday too, password cracking and password recovery. So this talk is just going to be a little bit more about the observations that I've seen in my limited data set. Than hard facts. Right, so that's the stage. You can do whatever you want with this information, of course. Hopefully improve your own dictionary attacks. So the data sets mainly come from something that we sell as security health checks. So these are similar to what we talked about yesterday. Somebody want to measure the password strength within the company. But instead of having a product, we have me. And so my consultants, they go out and they grab collections of hashes, and then they send them to me, and then I try to recover as much passwords as possible. And these are not done to blame anybody in the company or to figure out like who has the weakest password. It's basically just like a health check that you don't have too many weak passwords at wrong places. And then we do an educational effort when we talk about, like, let's say you have a company that have 70% of their password recovered, like a 200 people company. Then you're going to have to educate them a little bit about passwords, how you select passwords and so on. So this is the main goal, to educate people about how to choose better passwords and not to leave bad passwords in your environment. I can't share the data because it's super private for all reasons. And then as the patterns began to emerge, I became really interested. So a few years ago, I actually started to ask a few people, like, because, you know, I was working with IT admins, they were going to give me the passwords, and I figured, why not ask why they have chosen the specific passwords? So I pestered a few individuals over the years about their passwords, because obviously I had recovered it, and I tried to make it in a non-confrontational discussion about the password they have chosen, and then also took some notes, anonymous notes. So this is where these observations also come from. So the hashes that we recover are usually NTLM hashes from Azure Active Directory. Sometimes there are Kerberos tickets that we catch on the fly when we do pen tests. There are some Unix machines with different types of hashes, the good and the bad ones. And then some mainframes, because always good to do some mainframe stuff. And let's say maybe like half a decade ago, it was also kind of common to find a lot of web shells. And these web shells were protected by sometimes weak hashes, sometimes like less weak hashes. And then we helped them to try to recover these for forensics purposes, to figure out how actually the attacker was able to access, what they did with the web shell, and also this can be done to do a little bit of threat intelligence. So certain attackers have certain web shells, and then maybe we can reuse. They also, of course, like everybody, reuse passwords, right? So if we find the same web shell on different companies, we can probably track them using the hashes as well. So the password recovery is pretty much done on a gaming PC. We use Hashcat and John the Ripper. We don't have I haven't managed to convince the boss to buy a nice new graphics card. So we run this on 2 NVIDIA cards, basically. And then I added dictionaries over time. So I've done this for 7 years or so. So the dictionaries that I started with 7 years ago are not the same dictionaries that I normally run today, including my own improvements, of course. These are like the most common observed restrictions that I found in corporate environments. It's like minimum 8 characters, and then at least 1 capital letter, 1 numeral or a number, and 1 special characters. And this is basically the standard password restrictions. So this is what the persons that are going to have to select passwords are going to work against or within this key space. So capitalization, right? So this is usually taken care of when we run the recovery with permutation rules. The permutation rules will take the word list and then we'll do some capitalization in certain places. And so we don't actually have to add this into dictionaries so much. So this italic here is like answers from people what I talked about, right? So names and locations are very common, of course. Like your kid's name, your wife's name, or any kind of other name. And people answer, why do they do capitalization for names and locations? Because it's the way that we usually write names and locations with like a capital letter in the beginning. So then you will know that maybe if you should always try to have these things. And then if you want to add something, maybe you want to add it with capitalization if it's a name. There are also when you do programming and so on, you can have like certain words that are like concatenated together, but like they feel like, and then they can have like capitalization in the middle of the word, in the beginning of the word, and like at or other certain points. It's usually called camel or Pascal or snake case. And if you're testing a company that has a lot of developers, these types of constructed words are usually when you write functions or methods, and these trickle down into passwords as well. So if you want to test for developers, you can adhere to their kind of coding standard as well, which usually can be found on like intranets and home pages and so on. Special characters, right? So by far, like let's say like if we have a company of 1,000 employees and you get like you recovered 70% of the passwords, several hundreds of these passwords would have exclamation mark as the #1 special character. So you want to ask people why do they use this? And one reason is the location of the special character for exclamation mark. It's like pretty much the first special character on the keyboard, and it's also kind of independent on keyboard layout. So, and of course, the dataset again is a little bit limited to the companies that we have tested, right? It's mostly Scandinavian companies with some global subsidiaries, but it's also the questions, the answers are kind of like biased towards IT admins as well, which occasionally have to deal with different keyboard layouts. If you like, don't pay attention when you install a Linux or something, you end up with a US keyboard layout. The second most common was a little bit surprising for me. It was the @ sign. So I thought that the question mark was the second one, most common one, but no, the @ sign apparently is the second most common one. When I asked people about this, it's like, it's very easy to use the @ sign. We know where it is, even though it's not in the same place in different keyboard layouts, but you write it often when you write emails, so you know how to produce the @ sign at ease. It also seems to be something that people think are replacement friendly, like, so you want to replace one character in your password with something, it's very easy to replace it with an @ sign. It can also be used as a replacement for the actual word @ if you want to have like a phrase. So you add the @ there. And also when people are sharing passwords, it is apparently very easy to tell the other person that there's an @ sign in the password. I don't know why they said that, but you shouldn't share password, but it happens. All right, numbers. It was also part of the, so if people are allowed or like want to select more than one number, it is very common to select a sequence. And again, this is like also very easy to do on the keyboard to add a sequence to the numbers. Also there are other patterns that emerge, right? So maybe like a replication of the same number, like but only like in a or if it's actually like this one. So it's like, and this can be used to make a verbal mnemonic, like so 2 2s, 3 3s, 4 4s, 5 5s, right? So then you can remember your password much easier. So these are things that also very common observed in these types of recovery. And then we have conceptual complexity. So if you just look at a password that stems from some kind of pattern on your keyboard, it looks kind of complex. It almost looks like it was random generated. And people seem to, I don't know if they actually do this in a text editor first and say this looks kind of like complicated, or if you put it in a strength meter, it kind of maybe will actually give a high complexity, and then they use this. So this is extremely common as well, to find the patterns on the keyboard, and these are of course in a lot of the dictionaries, because it's very easy to generate the patterns yourself and then put them in a dictionary. However, sometimes when we test companies that have different keyboard layouts, for instance, like German has the Z and the Y switched, you might want to add some extra keyboard layout specific things into your to your dictionaries. And the same thing goes for Scandinavian countries. Like towards the right side, you have the special characters, O, and whatever they're called in other Scandinavian languages. So you want to add those too as well, because they also usually are included in when people try to, construct complex keyboard patterns. So, and I've improved my hit rate or recovery rate a lot by adding these things into the dictionary. Then there are, of course, like less common restrictions, which is pretty fun, right? So, so this one actually hit me. Because we had this restriction at one point in one of our services. You can't use the same character in a row, right? Twice in a row, right? This will invalidate the famous summer 2023 exclamation mark, but it will allow winter 2023 exclamation mark. It will invalidate winter 2022 exclamation mark. Because, so you take away some stuff, but not all of the bad passwords. And then, of course, there's also the restriction where you have some kind of filter that would check against leaks. That will then tell users that this password has been used in a leak. You shouldn't use it. So the thing about that is the leaks do not contain all the bad passwords. So you can still choose a bad password even if you check against the leak. So those are, so because a lot of, when I talk to the IT admins, oh, we checked against the leaks. It's just like nobody can choose bad passwords. Yeah, well, the leaks do not contain all the bad passwords. There's still some bad passwords that you can select.
And there are some good.
What?
And there are some good passwords in the leaks.
Yeah, of course. But then you can select them, right? Because they will trigger the leak detection. All right, so now into the more nitty-gritty stuff, right? So this was one of my first cultural discoveries, right? So these are predominantly Swedish companies, right? And then you have Swedish companies, when you have the password length restriction, it somehow, for some reason, it's hard to come up with the long passwords, right? So in Swedish companies, it's very, very common that you add a street address in the password. So you use a street address in password. It's it automatically includes a number usually. So that's fine. And then you just have to add an exclamation mark at the end. And maybe, start with a capital letter and then you're good. You get like a 23-character long password and then you're fine. So, of course, one of the first dictionaries I added was all the street names in Sweden. And then I got huge amount of hits in the password recovery. And then I figured out, sometimes I know which company I'm testing. Sometimes I just get like a list of hashes. But I was looking at specifically street names, and it turns out that location matters. So the street names could be like the company street name, it could be street name around the company, and also it could be street name where people live, right? So you get like suburb housing street names if you plot them on a map. So pretty interesting that people like to choose that. People also like to choose positive things, like vacation sites, countries, cities. These are usually not included if you dump a language dictionary and try to run that against your hashes. But it's very easy for you to generate vacation sites and countries and cities as well, and just add them to the mix. Car manufacturers, pretty common too, like especially if you have like a Porsche, it's kind of like a long name, Mercedes. Like the fancier the brands, the more common it is in the passwords. I don't know if they're trying to tell something about the password. Also, Italian designer clothes, Armani, that stuff is also common. Positive things. Visible or nearby locations. So common lunch restaurants, right? So I actually found Burger King, 1, 2, 3, 4. Of course, no problem. If you're in a company is located in a harbor, water theme like ships, boat, ferry, stuff like that. Landmarks. Turning Torso is like a famous tall building in Malmö, Sweden. You always find Turning Torso in Malmö dumps. All right, company-specific terminology, right? So if you're investigating a company that do hardware, right? You just want to add all their kind of product-specific technology lingo into a dictionary. Maybe you crawl it, and then you add it into the dictionary. You build kind of like a technical dictionary. Maybe suppliers, subcontractors. You run that, and you will find hammers and nails if it's a construction company. I call this, I don't know, it's like a duplication or multiplication, right? So if you can just add the weak password again in order to get like the required length. So this is also very common to do. It can be tricky for the rules that we apply to our dictionary attacks to actually catch the duplication or the multiplication, but it's not hard for you to script and add a little bit of a deeper recursion dictionary for your most common ones. So I'm getting short of time, right? Grammar. So when people are choosing phrases, they tend to choose grammatically correct phrases. And also they seldom include space, although most of the time it's very allowed in password to have spaces, but they try to think that space is not allowed. A sentence can be very short. I am really good. That is a very short sentence, so you can even brute force those sometimes. And even though they are grammatically correct, they usually don't add a dot at the very end of the sentence. Oh, this one is one of my favorites. Forcefully constructed, right? So I call this capitalization dependency. It's something that I made up yesterday when I do the slides. It's like you choose your capital letters in the way that you construct your phrase in order to sort of like have a dependency so you can easily remember it. So cautious, cactus, connections. All C's, seems to be easy to remember. And I have to make a confession here. I've done this myself. But much longer phrases, of course. And weird words. Physics words. In corporate environments, right? Apparently, it's important to be polite when you choose your password, even though you know nobody should actually recover or see your passwords. So if you look at internet dumps, they tend to be more violence, more erotic type of passwords. The university was the worst I've ever seen. It was obscene. It was almost like hard to actually read recovered passwords. But in corporate environments, it is important to be polite. And this is like, you should be polite at work and so on. So this is, if you're testing in a region, don't forget to include some neighboring countries' languages as well, right? So usually the local language and English are prevalent, like at least more than 70% of the passwords are usually in the local language or English. It's not too computationally expensive to add a different language. And when I talk to people about why they maybe have chosen a specific other language, they think of it a little bit like security or bioobscurity, right? They know another language. They think that if they just make the password in a different language, it's much harder to recover, although they actually didn't know that we would actually recover it, but they think. So I think it's, they said to me, it's a little bit like talking Swedish in Spain. Nobody understands what you're saying, which is not totally true, because if I were to walk next to them, then of course I would understand. So I had a huge success rate by adding all the Scandinavian countries into like the dictionary pool when I run for Scandinavian companies. Internet culture references, right? Movies, characters, actors, computer games, novel characters, usually like the main villain or the main hero, not like the lower types of people. And YouTubers, like I've found a lot of YouTubers as well. This one is really funny, and I'm very close to the end here. I had the opportunity to look at a few dumps from the east, like far east, east of Europe, and they seem to like symmetrical passwords in the east. I don't know why. I'm hoping my colleagues in Korea will give me some more data for this, but this is something that I observed from the far east. The mainframe, we talked about the mainframe before. It is still possible to choose bad passwords if you only have a maximum length of 8 characters. You can still select bad passwords. And it actually allows for a few special characters, but I rarely see them. So usually letters and numbers. If a person has more than one account in the environment, they usually do the same passwords, but just a little bit of a change. I call this password siblings, right? So this is where the multiplication duplication is very common. So what we do here, when we have run all the password cracking in like the AD domain, like one of the domains, we just run the same like extracted passwords one more time. And then you will find these password siblings as well. All right, honorable mentions, very close. If you're gonna invoke Eldritch Horror, make sure you spell that right. That was pretty funny. The second one, had no idea. This was captured by a dictionary. I think it might have been accidentally somebody pasted in a password into a dictionary. It was not like a leak dictionary, so it was really funny. And also, if you spell it wrong, you can still catch it by a dictionary just due to the rules. This is one of my favorites. This is a new thing. I'm not going to pronounce the Danish one, but these are something that I found recently, and this is something that I'm going to investigate. It's like nursery rhymes or things that you say in order to, like sex laxar I en laxask. I mean, that's like you're just going to tongue twisting this. So this is my new pet project. I'm going to add tongue twisters for other countries as well. I talked a lot about rules. These are the rules I use. You will get slides, I guess. And then I use also some of the standard rules. All right. Some creds. My colleagues, they help me. They give me the passwords. I can do all the fun stuff. All my interrogation victims should have a cred as well. Developers, open source of Hashcat and John the Ripper. Good stuff. Per, of course, and PasswordsCon for having me here. And boom. If you ever find me at CCC, I'm a regular visitor there in Germany. I hope they will go back to Hamburg because it's closer than Leipzig. You find me and I will treat you on a chunk, which is a special thing you drink there. Thank you.
Okay, so I'm going to say ask questions during lunch, and we'll just head straight over to Ashley.
I'm Ashley Shield and I'm from Maynooth University in Ireland, and so I'm in my final year PhD. I will be finishing October hopefully, and my PhD covers kind of a varied amount of topics. So I started off with the talk that I'm going to talk to you about today, which is about partial pins, and then I kind of moved on to cookie banners and privacy, and moved on then from there to kind of dark patterns. And I'm currently working on subscriptions at the moment. And yeah, but today I'm going to talk about partial pins. So me and my supervisor, we're aware of lots of studies. We were kind of aware of guessing pin studies. There was lots of password guessing studies. I know Max and Philip's study we were referenced in this particular paper. But what we hadn't come across was partial pins, and much discussion about these. We came across one study, but this kind of was basically focusing on kind of user-chosen pins and not kind of random pins. So we were curious about guessing pins via the partial pin, and how you would go about that, and is there any efficient strategies? Is it easier to guess a full pin based on guessing a partial pin, etc. So yeah, okay. Perfect. Okay, so today I'm going to discuss the partial pins backgrounds, because what I did notice that, say, I was talking in different locations, different countries about this, and the main question I got was people weren't actually aware of partial pins. I mean, that was Per's question when he asked me about this talk, was to kind of look into the background, and it's kind of interesting because that's what I discovered most, was that it seems to be mostly used in the UK and Ireland, with the exception of a few other European countries. So what we did was, in order to guess a pin by guessing partial pins first, we came up with 4 different strategies, and I'm going to go through these strategies in a little more detail. And then I'm going to, then I'm going to go through, I'm going to go through these in more detail. I'm going to show the results of these. And then what I'm also going to talk about is kind of whether or not we could actually implement the same kind of strategies on other forms of authentication, namely time-based one-time passwords. First of all, what are partial pins? So originally partial pins were used in phone banking, where the person on the phone would ask, in order to verify your account, would ask for a subset of your full PIN, so a random subset of your full PIN, in order that he or she won't actually find out your full PIN, and to prevent a replay attack. So, however, with the emergence of online banking, this kind of method and with all the advantages of being online, brings, they no longer appear to fit their purpose, and they kind of seem to provide mostly security theater. So when I was starting this project, for example, I personally, because I'm from Ireland, so I have a bank, and it was currently at that time using partial pin system, and I kind of thought myself, oh, that makes sense, as in that's more secure. And then when I went looking into this, I was really interested to see how unsecure it is in comparison to a full pin. I don't know what it is. I kind of logically thought that it would be more secure. But their main purpose really is to protect from key logging and over-the-shoulder attacks. But as we shall see, many roads lead to Rome. Okay. So as I mentioned in the beginning, partial pins appear to be mostly used in the UK and Ireland. But as you can see from this table, Germany is up there, Canada also is up there. And this here on the right is a login for a Polish bank. And also when I was in Holland, one of the person in the audience said that they had come across this partial password system in Holland as well. But I don't actually think it was a bank. So it appears to be it is mostly used in the banking sector. And when I went to ask, because I was curious and I wanted to find out what ChatGPT would think if it was used in other locations or what other, where it's used. And it didn't seem to understand the concept of partial pins or passwords. I tried different variation of the language or the words. It's kind of identified it more as an extra code that you would input for certain banks in different countries as well as your already password, not a subset of your password. So this kind of highlights that it's not, that common. So these days, if pins are used, they're kind of used more as a second form of authentication, which you can see on the table. You have a second credential, could be a question or another pin, or date of birth as well as up there. So AIB, as I mentioned, is on this list. That's an Irish bank. And up here, they have a password length of 5 with a challenge size of 3. So that's 3 digits from your 5 personal access code, is what we called it in AIB. So that means, since this survey is done in 2012, so since then, AIB have actually stopped their partial PIN system. So now you have to enter your full personal access code. So what's interesting to note is that they're the only bank that's actually done this. So the rest of the banks are still doing this. And I figure it's because there's second forms of authentication that they're not changing the system. So I was kind of curious. I'm not sure why AIB actually changed it. I wasn't able to find out. Okay, so now I'm going to talk about our attacker strategies and our in the wild scenario. So this is a very low level in the wild scenario. And this sees our attacker Eve, who is played by me. So she has access to Bob's phone. She could be living with them. And so she decides to play the long game, and she's going to try and get into Bob's bank account by guessing his partial PIN incrementally. So she's going to try every day, a few times a day, although I don't think, sometimes there isn't a rate limit on these partial pins. As we found out ourselves, that it's not actually just 3 attempts, it can be more. So she has a few attempts each day before being locked out. And she's going to try again the next day, and so on. And each time, she's going to rule out incorrect guesses from a pin list. So the pin list size can depend on the length of the code itself. So it could be for a 4-digit code, it could be 10,000 digits, or then for a 6-digit code, it could be a list of 1 million. So if she gains access with the correct code, she has now those digits of the full PIN. And she can eliminate all the ones that don't match that partial PIN in order. So in the case of a 5-digit PIN, say for example AIB in the old days, if she gets the 3 digits partial PIN, she now only has 2 digits left to guess, and that's basically a cakewalk compared to 5. Eventually she'll guess the whole PIN with enough patience. So kind of in abstract terms, this is what's the guessing game for a partial PIN. So your bank is going to choose the secret, and that's our PIN. And our pin list is the set of all possibilities ranging from 000 to 999. Our guess is our partial pin, and it's for 2 random positions. And the response to this depends on the secret and the guess. And that means if it's a successful login or not. And then after guessing, the list of the remaining numbers is that set here. And of course, if the attacker has already snooped information, you can start off with a different set size. So we came up with 4 different strategies. We have the max method and the educated guess method. These 2 methods are relying on a pin list to make their informed choices of guess. Random and round robin don't use a pin list, and the reason we have these is more of kind of a base method to kind of compare the other 2 methods. So the max method is, it uses the pin list to find the frequency of the combinations for the positions of the partial pin that's being requested. So the combination with the highest frequency is picked. And then we have the educated guess is kind of looking at more the distribution of the digit combinations for the positions requested. So for example, if the second and third digit has requested has 50% of the pins has 77, 25% could have 78, and 25% could have 79, it's going to pick 77. The random method is, as the name suggests, is just going to be picking random numbers, and it'll eventually guess all combinations. And then the round robin method is, it kind of starts by picking for the digit 0, and the next guess is going to pick 1 and so on, ending at 9. The only issue with the round robin one is that it usually fails on n choose n. So, you know, it'll only guess 0, 0, 0 or 1, 1, 1, etc. So that's kind of acting more like random, and it kind of takes a long time. So we plotted all the results. We did many graphs, and this is kind of one that shows all the methods on one graph to kind of compare. So on the bottom, we have the amount of guesses on the x-axis, and on the y-axis is our pin list. So the first strategy there is in red, and you can see that it has a success around 70. And then it's educated guess is next, and it's roughly similar. And then we have robin, which kind of takes a long time, but it kind of guesses just over 300. And then random is the worst, guessing at over 300 guesses to get. So this is for a pin size of 4 and a partial pin of 2. So in this example and the ones to follow, the strategies kind of discover the pin in the same order. It'll always be max strategy is the best, followed by educated guess, and then robin method, and then random. So looking at the max method in more detail, you can see that at around 300 guesses, you have a 25% chance of guessing a pin in around around 3 months. So that's for a full pin of 6 and a partial pin of 3. And then kind of comparing to a full pin of 6, which is 6 choose 6, you have this for the same 25% chance, it would take about 250,000 guesses and would take roughly 250 years. So it kind of further emphasizes why full pins are better. So, if we go back to Eve, she would have, say, a 50% chance of guessing Bob's pin in under 5 months, and practically 100% chance in over a year. So these are kind of some more graphs and more details for different full pin and partial pin size. So we have full pin of 6, choose 1, up to 6, choose 3. So for the first ones, you can see that the max and educator guess are all kind of behaving the same. And then as you go down towards up to 6, choose 4, 6, choose 5, and 6, choose 6, they're eventually kind of all acting the same. So it kind of essentially the full pin at 6, choose 6, it doesn't matter what method, they all kind of guess at the same time. Okay, so I mentioned time-based one-time passwords at the beginning. So this was kind of like a thought experiment that we were kind of recently thinking about whether could we use the kind of same technique as such to guess time-based one-time passwords. So essentially the principle is the same, but the pin list is obviously much bigger. So like, you know, I think most people would know what time-based passwords are about. So you have a shared secret and the current time to generate a unique password. And that changes every 30 seconds. And it's synchronized with the server that verifies the user's credentials. So if we compare this with our guessing partial pin scenario, the secret can be compared to the pin, time can be compared to the partial pin, and the hash can be compared to the digit selection. So we assume that the secret part is 256 bits. So there are 2 to the 256 possibilities. So this would make a really big list. And so we can take this example as our pin list. So if this is in the case of snooped information, and if we guess one of these pins, we're crossing off all these kind of as we go along. So that's the probability that the key is still on the list after so many snoops. When you guess a snooped piece of information, you are getting rid of a huge chunk of the list as you go along. Okay, so say now I'm sitting on a train and I've progressed from trying to guess my flatmate's bank details, and I see the person beside me who has an authenticator app open. They could leave it open on the table for say 3 minutes and I could get 6 time-based passwords. So I mark the time and the codes, and I can look up the hash, and then I can get this here and hash each of the keys in order to see if it matches this code. So then this kind of is saying how many snoops we'd need to kind of guess the pin. So like in this particular case, the number of snoops needed in this case would be around 13. So given the size of this list, it's not very practical computationally, and also, but it does kind of match our partial pin framework. But another point to make out is that the key size can also vary and depends on the authenticator itself. Okay, so in conclusion, partial pins are not great. So we've looked for different strategies of guessing a pin in a system from M digits from M are picked, and we've looked from sizes 1 up to 6 partial size. And the number of guesses increases with both N and M. We've also seen that it's kind of possible that you can have a reasonable fraction of pins with about tens to hundreds of guesses. So from a user's perspective, though, I'd say partial passwords are kind of crap. For myself personally, I would find it hard to remember specific positions of a pin. If you know, say even my phone number, you can list out your phone number, no problem. But then if somebody says, well, what's the 4th digit of your phone number, you kind of go, or you would have to maybe write it down. I mean, I've had to do this before. I've had to write down my PIN in order to get the positions for inputting into the partial PIN banking app, for example. And that in itself is kind of a security risk as well. And from, you know, it was interesting to listen to Kirsty's talk yesterday about kind of universal design, and it kind of highlights how unusable more than anything the system is. What I would love is to kind of talk to anyone else here and find out if anyone else has actually heard of partial PINs, because in their own countries or for partial passwords. I haven't really come across that. So I would like to talk to anyone about that. I would also, this is a QR code that links to my website with the Advanced Center for Research Training, and that's where you can find my contact details or my Twitter handle there. And that's all for today. That's my talk. If anyone has a question or if they'd like to talk later, I'm happy to talk.
I'm first. Many years ago, I think I got contacted by a guy in Kuwait, and I think they had partial PINs for online banking there.
Oh, I haven't
and
heard
they
of
also
Kuwait.
had entry using a randomized virtual keyboard on screen. So if you were doing some kind of sniffing or watching off the screen as well, you know, the number 1 wouldn't be in the same place each time they were to log in.
Yeah, I think I saw that, yeah.
So when you submitted this, I was really curious about listening to it, because again, partial PINs like that, I've never seen it here in Norway, as an example. And I'm curious, asking the audience, other countries where they do that.
South Africa has it for almost every single bank, so, but we follow the British system. So.
Yeah.
Oh, so it's South Africa, yeah. Yeah, cool.
2010 Romania, Austrian banks have the same system. Also the scrambled PIN pad. So
on screen, yeah.
Yeah. But they got rid of it, right?
I have no clue. I can tell you that now in Germany, partial PINs are still a thing as a validator, so as a second factor.
Yeah.
But not for banks. I've seen it for credit rating agency or similar.
Okay, yeah.
Ukraine, I've never seen anything like that.
Yeah, most places haven't seen it, so that was the most interesting thing I found, was that people is like, what the hell is a partial PIN? And yeah, even the kind of logic behind it, it's kind of interesting to see why they kind of used it. You know, it kind of makes sense in the context of the person on the phone, but even that's not really safe, right?
Even the first time I heard about partial PINs, I still can't really understand why anyone would design such a system.
Yeah.
It just doesn't sound secure, and I can't also, you know, from a usability perspective as well, as you said, you know, which is, what is the 5th digit in your phone number? You have to think about it. That's not good usability. It should be just like instant.
Yeah, and also I think you can't, well, I heard that they're not actually hashing the pins, but you definitely can't hash partial pins. There's too many. There's too many combinations.
The partial phone number is something that is quite popular. Like, please type your 4 last digits of the phone number.
Oh yeah, but
it is something that is very popular.
That's similar, but it's always the last 4, isn't it?
So as part of an authentication process.
Yeah.
Then you get SMS.
Yeah.
Oh yeah, that one.
Yeah.
Of course.
In the U.S., it's fairly common to use the last 4 digits of our Social Security number.
Yeah.
For things.
And then we have a totally new topic about Social Security numbers. In Norway, it's a publicly known algorithm to generate Social Security numbers. I can tell you, I'm born on September 10, 1971, and then you can go online, use your free generator to generate the approximately 100 and something Social Security codes that are valid for a male born on that day, and one of them is me.
Yeah, there are a lot of the Estonian national ID numbers also contain birthday and gender and just a sequence number beyond that.
Yeah.
But in the U.S., the social security number is supposed to be sort of quasi-secret for people because it's used as an authentication secret in a number of contexts, but in a number of places use the last four.
And it's even crazier here in Norway because it was never supposed to be a secret, but even today it is being used as a secret.
Yeah.
So, yeah.
Yeah, so talking about SSN or partial pins, that is used for by cell phone providers a lot when they are using like family accounts to kind of share details. So we did a study on like cell phone providers' privacy, like security, and that was very concerning because in a family, not everybody is like a family, though it is supposed to be. So like even in friends, they are exchanging these last 4 digits of social security, which is used for several companies as partial pins. So that really compromised the security because, for example, I am in family plan where my friends are there. They are not family, so that is concerning. In India, they don't use partial pin. Now they have, because there have been a lot of issues during COVID, so now they have made it like really secure, but it is not usable at all. They have made like 2 passwords which you need. One is account password, one is like just to log in password.
Yeah.
And that is actually creating like how much security is needed. Like even for me, it is completely unusable. And when I'm trying to access my bank from US, it literally stops. So my parents have to go to the bank. They do physical authentication. So from the looking to the other end, this is definitely great work. And but from the usability side, for me, it is like I cannot even use my funds for 7 days because it requires physical authentication. So that's what is happening different.
Like even the four last digits of a phone number or a social security number, like 4 digits is really easy to remember. You know, you can kind of run in your head. You only have to hear them once if you heard it from someone. Yeah.
Well, the other problem with a partial password more generally is that if they can verify you on a partial password, you have a pretty good idea that they haven't salted and hashed the password.
Oh yeah.
Absolutely.
Yeah.
Another question, just a comment. I googled it. The ING Bank in Germany, they stopped it last year.
Last year. That's interesting. Yeah. I'll take note of that definitely. Yeah.
And Ashley, you're Irish, right?
Yes.
Yeah, so we can go to lunch when Ashley will allow us to go to lunch. So, no questions for Ashley? Nobody cares? Okay, obviously, people want lunch.
Yeah.
Can we take lunch?
Yes, of course. And sorry about the technical issues at the beginning.
And I already tweeted out amazing slide layout.
Oh yes, I was sure it was going to be used.
You win the award for the most original slides this time.
I was paranoid somebody else would have the same template, so I'm very happy.
Okay, thank you again, Ashley.
Thank you.
Okay. Then we are ready to get started again. And it's a pleasure to welcome Collins to talk about one out of many, many favorite topics, pin codes. And this has also been partially talked about before. So I'm looking forward to learn even more about this topic now. Take it away, Collins.
Thank you so much for the very kind introduction. Good afternoon, everyone. I hope you are all enjoying PasswordsCon so far. My name is Collins, and I'm a third-year PhD student at the George Washington University. On behalf of my co-authors, I'm very excited to present to you our recent work on the security and usability impact of upgrading pins from 4 to 6 digits. This paper was published at Usenix Security last year, but I also added some exclusive content just for PasswordsCon. So 4-digit pins have long been the default method of authentication on smartphones. However, recently companies like Apple have moved from requiring 4-digit pins to 6-digit pins, citing that this improves security. Well, but does moving from 4 to 6 digits really improve security for human-chosen pins? What impact does this even have on usability? All these questions inspired us to do this research. And fundamentally, we ask, was this a good thing, both from a security perspective as well as a usability point of view? So more specifically, we were interested in addressing 3 research questions. Number 1, how do users select a 6-digit PIN, having previously selected a 4-digit PIN? We're also interested in how the upgrade process, as well as the justification given, impact security and usability of selected pins. Lastly, we were interested in understanding how predictable a user's 6-digit PIN is if their previous 4-digit PIN is known to an adversary. So to address our research questions, we conducted an online survey where participants first selected a 4-digit PIN they would use to unlock their smartphone. It's important to note that all participants selected a 4-digit PIN under the same exact conditions. Thereafter, we asked participants some device usage questions, including the number of devices they own, any authentication mechanisms they use, and this was mostly a distractor task before proceeding to the next task, which was essentially selecting a 6-digit PIN. And so during the course of selecting a 6-digit PIN, we tried to vary these instructions just to see what impact this would have on both security and usability of selected 6-digit pins. And so this message here is essentially what differed across the 5 different treatments, and I'll explain this a bit more in the next slide. After recalling their 4-digit PIN, our participants selected a 6-digit PIN. We then asked some follow-up questions, including their PIN preference, before finally asking participants to recall their 6-digit PIN at the end of the study. When selecting a 6-digit PIN, we had 5 different treatments where we varied the upgrade message. So for the neutral treatment, we used a very neutral message where we just asked participants to now select a 6-digit PIN before they could advance with the rest of the study. For the upgrade treatment, we asked participants to imagine that their smartphone's operating system was upgrading, and now instead of a 4-digit PIN, they needed a 6-digit PIN to protect their smartphone. For security, we told participants that their 4-digit PIN was insecure, and now to protect their smartphone, they had to select a 6-digit PIN. For the bridge treatment, we told participants to imagine that someone had learned their 4-digit PIN, and so they now had to select a 6-digit PIN to protect their phone. And then lastly, we had a no subsequence treatment. And for this particular treatment, we used a very similar message to the neutral treatment. But in addition, we also had a block list in place where we prevented participants from using any subsequences of their 4-digit PIN in their 6-digit PIN. So for example, if a participant used 1, 2, 3, 4 as their 4-digit PIN, they could not use something like 0, 0, 1, 2, 3, 4, 1, 2, 0, 0, 3, 4, 1, 2, 3, 4, 5, 6 as their 6-digit PIN. And there was a couple of more, but these are just a few examples. So in terms of demographics of our participants, we recruited a total of 1,010 participants from the US, and we used Prolific to do this. So for those of you who may not be aware, Prolific is just a crowd recruitment platform where you can use to recruit research participants for studies. So we ensured that each of our 5 treatments was assigned at least 200 participants. And lastly, it's important to note that participants actually use their own smartphones to both select and recall PINs in our study. So what did we find? So I'm going to start by presenting some of our quantitative security findings before sharing some of our qualitative findings regarding user perceptions as well as preferences about PINs. So in presenting our guessability results, we first focus on an untargeted attacker. So we use the untargeted attacker to guess both 4- and 6-digit PINs. And for this attacker, we assume that they have no prior information about the victim whatsoever. And so a more targeted attacker might know things about the victim, for example, their birthday, which might improve their guessing performance. But for this specific scenario, we assume the attacker has no information whatsoever about the victim. This attacker also uses data sets collected from previous work when trying to do the guessing. And the way they do the guessing is the attacker first looks at the most frequent PIN that appears in previous data sets, and that's the first guess. And then the next guess is the next most common PIN, and so on and so forth. So in terms of our guessability results, the x-axis represents the number of guesses made by the attacker, and we have a cutoff of 30 because that's kind of like the upper limit on Android devices before significant delays start to occur. The y-axis, on the other hand, represents the fraction of PINs that are guessed. And so the more PINs that are guessed, the worse they are from a security point of view. And the lesser the PINs that are guessed, the better they are from a security perspective. And so this is ideally what we want to happen. So this graph here shows how an untargeted attacker performs when guessing 4-digit PINs across the 5 different treatments. And just as a reminder, participants selected 4-digit PINs under the same exact condition. And what we can see here is that the guessing performance was comparatively similar across all the treatments. And we found no significant differences when we ran a chi-squared test. When we compare the guessing performance of 4-digit PINs to 6-digit PINs in the neutral treatment, which we kind of like used as a control experiment, the performance again is mostly the same. Those 6-digit pins appear to be somewhat less guessable when making up to 30 guesses. However, when making up to 10 guesses, which is kind of like the cutoff for iOS devices where the device can lock or all data gets wiped off, the attacker guesses comparatively the same number of 6-digit pins in the neutral treatment compared to most of the 4-digit pin treatments. And the key takeaway from here is that 6-digit pins only seem to offer a very small security improvement compared to 4-digit pins. But at the same time, as we are going to see later, they also seem to add some additional usability burdens that might actually not be worth these upgrade efforts. And so this is something that we encourage system designers to consider before forcing users to upgrade. We're also interested in the impact of the upgrade message on the security of selected 6-digit pins. And comparatively, a small number of pins, of 6-digit pins in the security and breach treatment were guessed by the untargeted attacker. This is in comparison to the neutral and upgrade treatments, where a comparatively higher number of pins were guessed. This implies that security-oriented upgrade messages can indeed nudge users to select more secure pins. But perhaps counterintuitively, the pins in the no subsequence treatment seem to be the most easily guessed, despite the block list that we had where we prevented users from using any subsequence of their 4-digit pin in their 6-digit pin. And this is potentially as a result of user frustration after they could not use any of their 4-digit pin subsequences in their 6-digit pin. And so a few of them ended up just resorting to common, more easily guessable pins like 1, 2, 3, 4. And this just shows that well-intended security measures can sometimes fail to achieve desired security outcomes. But nevertheless, more security-oriented upgrade messages seem like a promising way to nudge users to select more secure pins. Besides the untargeted attacker, we used a targeted attacker to measure the security of 6-digit pins. And for this particular attacker, we assume that they know the victim's 4-digit pin in trying to guess their 6-digit pin. And so the initial guesses made by this attacker are very targeted in the sense that they try to do basic heuristics on the victim's 4-digit pin, for example, appending digits to the end, prepending things at the front to see if they can actually guess. And if they are not able to do that within about 20 guesses, this attacker resorts to guessing pins in a decreasing frequency order, similar to the untargeted attacker. We also assume that this attacker is aware of the block list that was used in the no subsequence treatment, and so they don't try to make guesses for pins that the participants could not have selected because they know they were blocked. So to model our targeted attacker, we first analyzed 4 to 6-digit pin transitions and observed that appends were the most common. So like most participants tended to append things at the end of their 4-digit pin when selecting their 6-digit pin. Particularly, a majority of participants chose to append the first two digits of their 4-digit pin in their 6-digit pin. So for example, if someone had 7733 as their 4-digit pin, most of them ended up with 773377 as their 6-digit pin. Several participants also appended the last digit twice. And so if someone had 4576 as their 4-digit pin, most of them ended up with 457666 as their 6-digit pin. Lastly, many participants appended the last 2 digits. So for example, if someone had 5109 as their 4-digit pin, they almost always ended up with 510909 as their 6-digit pin. We also noted a number of common pins selected by participants. The most common pin particularly was 1, 2, 3, 4, 5, 6, which is, just as an increasing pattern on the keypad, followed by an inverse of this pin, which is 6, 5, 4, 2, 3, 1. The pin 159357 was also a very common pin that you observed, and it also forms a pattern on the keypad. Lastly, we also had some participants prepend digits at the front of their 4-digit PIN when choosing their 6-digit PIN. And most of these prepends were 00, and so if someone had 9997 as their 4-digit PIN, they almost ended up with 009997 as their 6-digit PIN. And our targeted attacker therefore takes advantage of these common transitions when guessing the victim's 6-digit PIN, of course specifically excluding the specific transition that was used by the victim to avoid overfitting. So this is the untargeted attack that we saw earlier, and this is how the targeted attacker performs. So we can see quite a huge bump in performance across all the treatments, maybe except the no-sub treatment, since the attacker could not, since there was essentially no relationship between the 4- and 6-digit pins. And interestingly, in the upgrade scenario, which is the most relevant to the iOS upgrade scenario, pins here were the most easily guessed, with over 25% of pins guessed after just 10 guesses. And the key conclusion from this is that many users tend to select 6-digit pins that are related to their 4-digit pins, and preventing this relationship sometimes actually resulted in worse outcomes. However, we believe that if upgrades are indeed necessary, it's important to encourage users to protect their seemingly obsolete 4-digit PIN, as they can clearly leak information about participants' 6-digit pins. We further asked participants about their perceptions regarding security, memorability, and ease of use of both their 4-digit pins as well as their 6-digit pins. So for security, most participants perceived their 6-digit pin to be more secure than their 4-digit pin just because their 6-digit pin was longer. And this is particularly interesting because from our guessability results, we actually noted that 6-digit pins were not that meaningfully more secure than 4-digit pins. In terms of memorability, most participants across all the treatments perceived their 4-digit pin to be more memorable than their 6-digit pin. So this kind of just shows that users do indeed believe that 4-digit pins are actually more usable in comparison to 6-digit pins. Similarly, an overwhelming majority of participants across both treatments perceived their 4-digit pin to be easier to use compared to their 6-digit pin. We also inquired about which of the two pins that participants would actually prefer to use on their smartphones outside the study. For the neutral treatments, so neutral and upgrade, most participants preferred their 4-digit pin. However, in the more security-oriented treatments, where we explicitly told participants that their 4-digit pin was insecure, more participants seemed to indicate a preference for their 6-digit pin. And this was mostly because of them pointing to security benefits. We also asked participants for their reason for their preferences as a follow-up to the previous chart that I just showed. And most participants that preferred their 6-digit pins often pointed to their security benefits. So for example, P11 said that I feel like the longer pin is more secure just because it has more digits. And again, as we saw in the guessability analysis, this is not necessarily always the case. On the other hand, participants that prefer 4-digit pins often pointed to their usability. For example, P1 said that I would use the 4-digit pin over the 6-digit pin because it's shorter and quicker. I don't worry about anyone getting into my phone. So just to summarize and wrap up, we conducted a study to explore the security and usability implications of upgrading pins from 4 to 6 digits. We found that most participants perceive their 4-digit pins to be more usable in comparison to their 6-digit pins. At the same time, most users seemed to falsely believe that 6-digit pins are more secure than 4-digit pins just because they have more digits. We also found that most users tend to select 6-digit pins that are related to their 4-digit pins, and preventing this relationship didn't always necessarily improve security. However, we also found that security-oriented upgrade messages actually seem to have some slight benefit in terms of improving security for the 6-digit pins. However, our overall takeaway from this was that encouraging users to select a secure pin once, whether of 4 or 6 digits, is likely to be more beneficial than forcing unnecessary upgrades. Of course, this was not work that I did by myself. I had a lot of amazing co-authors, including Philip, who's right here in the audience. And yeah, I think I'm ready to take questions.
Thank you, very interesting. I'm just curious if you are already looking perhaps into not going from 4 to 6, but the length from the beginning, perhaps deciding the quality of the pin, as in, for example, if I am asked to choose a 4-digit pin, then it's very tempting to choose a year. If it's 6 digits, maybe I will do a day, 1 month, year. But one time I was asked for 5 digits, like not more, no less, exactly 5, and then you realize what is a bad choice that you can make with just 5 digits.
Right.
So maybe 5 is somehow better than 4 or 6?
Yeah, that's a very interesting question. So I'm actually not sure it would necessarily lead to security benefits. At least we thought, for example, blocking people from having any subsequence of their 4-digit pin would have security benefits, but it just led to user frustration. And I think more people, because they had more digits to remember, they gravitated towards even more easily guessable things. So we had like people move from, maybe if we had actually not prevented the relationship, they would have selected a slightly more secure pin. But then because we prevented that, they ended up selecting 0, 6 times. And so I'm actually not sure it would improve security, but that would probably be an interesting study to do.
If you go 15, 20 years back in time here in Norway, you were not allowed to pick your own pin for debit or credit cards at all. And one of the first credit card companies from Sweden that introduced the user choice here in Norway, they ran a marketing campaign saying, now you can pick your own PIN code for your credit card, so now you can finally use 0000 or 1234. The employer of a friend of mine, they would either cut ties to the company or they had to fire my friend from the company just because he knew me and I wrote a post saying, you idiots. So, yeah. There are many questions on this. I would also like to, since I'm the organizer, I get to ask. But this is a question for you, Collins. But this is also partially for Ashley and also for Philip and Stefan and Max as well. I'm really curious because I haven't seen it yet. So this is also sort of a new research topic that somebody can grab. I'm really curious about if you were given your PIN code, where did you get it from? That includes physical access card, were you given a PIN code from the reception? Did you get a PIN code for your different debit and credit cards, or did you have the option to pick one? And if you had the option, did you use it, or one that you had selected yourself? 15 years ago, the local newspaper here in Bergen, I spoke with them, and they went out on the street and asked people about passwords and PIN codes, just like interviewing a couple of people in the street. And one of the quotes I remember there was actually a TV personality from a Norwegian news channel. And she said that I just can't remember my PIN codes at all. But there is one PIN code that I never forget. That's the PIN code for my mom's debit card. Which was sort of funny, maybe not politically correct to do today, but I did that anyway. More questions for Collins. Raise your hand. Jim.
So I realize that the amount of data that we have about distribution of 6-digit pins is not as good as 4. But is there any indication, I mean, you'd expect that if you might see some skew in the distribution where you might have the fourth, fifth, and sixth digits all the same because of people doing one of the things that you described.
So
Yeah.
not so great, but like what people have done in the past, and also what we've kind of like did in this study was to just extract like pin sequences from leaks such as the raw queue. And so if we saw like some consecutive 6 digits, that qualified as a potential pin. And so that's what we ended up using. And you know, when you look at data sets like that, you also like notice very common patterns. So things like 1, 2, 3, 4, 5, 6 are very common. You know, like just the same digit 6 times are also super common.
It seems like that might be one of the limitations of that kind of a data set for 6-digit pins is that you know it wouldn't expose those kinds of things.
Yeah, and you know, running this experiment is usually very expensive, but it would actually be amazing if someone could go out there and collect lots of these 6-digit pins, because at least that's something that doesn't exist for 6-digit pins. We have something for 4-digit pins, but we don't have anything like that for 6-digit pins. So that would be interesting, like a large data set of 6-digit pins actually selected by users.
Yeah.
I think his hand went up first.
So my question is, in your instructions, before changing to 6-digit pin, you asked the user to first enter the 4-digit pin again.
Right.
And then enter the 6-digit pin.
Yeah.
Do you know if that had any impact on the 6-digit pin that was selected?
Yes, so we purposefully had like different treatments, and we kind of like varied the upgrade message, and that seemed to have an impact. At least the pins that were selected in the more security-oriented treatments tended to be slightly less guessable compared to participants where we were like, hey, imagine your smartphone's OS is upgrading, you now need to select a 6-digit pin. And so yeah, we kind of like noted some impact of the messaging in terms of the 6-digit pins that were ultimately selected.
But did they always have to enter the 4-digit pin first and then change?
Yes. Yeah, they had to enter the 4-digit pin before selecting a 6-digit pin, yeah.
Thank you. Why do you have this result? Maybe the conclusion is wrong. Maybe 6-digit pin is more secure as it's supposed to be, but the people behavior by default when they switch from 4-digit pin to 6 is not good enough. Maybe the thing is in the behavior. And do you think you can replicate this result if you go further to 7 and 8-digit? Sorry, 2 questions, but...
Yeah, so can you please repeat the first question? Yeah.
Okay, first question. Why do you think you have received this result?
Yes, so in terms of why we received this result, so I mean, this is how participants behaved, and it's not, actually we thought 6-digit pins would be meaningfully more secure than 4-digit pins, but for the few guesses that you can actually make in a throttled scenario, which is typically the case for mobile authentication, just happens not to be the case. Maybe if you make up to 100 guesses, maybe 6-digit pins might be more secure, but it doesn't really matter because you can't do that. And so it's what we found.
Do you think the result will replicate if you increase the 7-digit and 8 and 9, or will it be a drop somewhere like 7 is still not secure, but 8 is like way more secure?
I would actually be very interested in doing that study. I don't actually have no idea what would happen, but that would be a very interesting study to do.
I think with 8, you would have a mirroring of 4.
But twice.
Yeah.
Only if you upgrade from 4. Yeah. But if you haven't had a 4 pin, and you still need to come up with a new 6 or 7.
Okay.
Sorry.
When I've been traveling to different countries, I've been asking, now raise your hand if you have a PIN code which is not 4 or 6 digits. So there are some paranoids in here.
Very interesting.
Because that is just one of the many fascinations of mine. People are not aware that it is possible to do anything else than a 4 or 6-digit pin on a phone. They've never been into the settings. So I tell them, well, did you know that you can actually set up the number 1 as a PIN code on your phone, and on the lock screen, when I swipe to the right on your phone, then based on the layout, the design, I don't know if you're using 1, 2, 3, 4, 5, 6, or maybe 15 symbols or numbers in your PIN, but you are only actually just using one. So the UX turns a little bit worse. The security improves sort of like a lot, because for an attacker, it's much harder to figure out what are you actually using. And it could be as simple as the letter A or the number 1. So that's a thing that I think Alcomsoft is one of those that have mentioned that earlier, a long time ago at PasswordsCon as well.
But,
Max?
Just a comment for this,
Yeah.
because if you check on the iPhone, I have a 6-digit,
yeah.
and there are these empty little circles indicating the...
Yes, that's something.
Because Apple is UX focused.
Yeah, actually, that's something that I've always wondered. Like, is it actually beneficial to like show like the length of the pin? Like, maybe that actually helps an adversary because they know what they can actually guess.
Yeah, but if Thomas changes that into a 7-digit pin, then you don't see the small circle showing that you have 7 digits. Then you will just see a field and an OK button that you have to press when you have finished typing in your PIN or password. Yeah. So it's a very subtle, but it's there. It's a UX design which is really interesting. Yeah. More questions? Sanshari?
Yeah. Oh, go ahead. Sorry, you got it. No, go ahead.
First of all, so do you guys were you guys doing the guessability manually or?
No, so we wrote a bunch of Python scripts to do this automatically for us, yeah.
Okay, and which was based on the pins.
Yeah.
And the other thing is, what was your, why did you decide on learning about pins and particularly 4 to 6? I know there were changes made to the Apple or Android as well, but what was the motivation particularly looking into it? Because I agree it is based on the users, but I also wanted to think about your hypothesis and your team's hypothesis in that.
Yeah, so I think this was just random chatting with my advisor one day, and he was like, there's this change that Apple has made about switching pins from 4 to 6 digits. Maybe it improves security, maybe it's not. Maybe it's something interesting that we should do, and we went ahead and did it. So it was actually mostly motivated by Apple deciding to, by default, recommend 6-digit pins over 4-digit pins after, I think it was an iOS update which just switched that by default. So it was mostly us being curious about whether that had any security benefits. Because I think there was a blog post by Ars Technica that essentially said that, more options means the pins that are going to be selected will be more secure because, 6-digit pins has more options, so it's hard to guess. So it was mostly the Apple transition that motivated us to do this.
Yes, and also they mentioned it in their Apple conference that they are doing it because it is more secure and they stated it. So have you reached out to them given your work?
Yeah, so actually when I presented this at Usenext last year, I spoke to a few people from Apple. I think they like our work, but they, we've also done other studies in the past for mobile authentication. They listen to our talks, but they go ahead and do the exact opposite. maybe they know something we don't. Thank you.
Yeah.
Okay, then we will do a 10-11-minute break and we get ready for Mackenzie. Thank you again, colleagues.
You're welcome.
So now you
Okay.
can go to the room.
All right. Yep.
And yes, this is Mackenzie, and he's absolutely not from Australia, which I learned probably on Saturday evening when quite a few of us were watching Eurovision Song Contest on TV. Yeah, that's my apology, and the rest is yours.
Awesome. It's great to be here. Thanks, everyone. I do feel like I'm a bit of an imposter here, as I don't have a PhD. I'm not getting my PhD, but hopefully I can still intrigue you with my presentation. So I'm going to talk about looking at how attackers really find and use secrets in exploits. So I will do this by combining some research that we have done and then pairing it up with real-life attacks that have happened that have followed those trajectories. So first about me, I'm from New Zealand, from Aotearoa, not Australia. I live in the Netherlands now. I work for a French company. It's a bit of a weird mixture. You can find me anywhere at the social handle @AdvocateMac. And if you want to listen to me for hours, my mum's favorite podcast is The Security Repo, which is my podcast where I interview mostly hackers about what they do. So just to start, I'm sure this slide is probably redundant for most people here, but I'll go through it just in case. So I will be referring to secrets, but the secrets that generally I will be referring to are digital authentication tokens, and these are typically used by machine-to-machine identity. So these aren't passwords. They could be a username and password for a database, but they're made to be used from other machines to other machines. So they are generally not created by humans in terms of memory passwords. They are usually not used by humans, but humans touch them. And that's where the problem tends to come in, is when humans interact with these. So because they're made to be used from other machines, they have a high probability of ending up inside source code. It's probably the #1 place of where these end up. And they are very, very sensitive. They are typically some of the crown jewels that any organization will have in them. So I just want to start quickly to take a look at how modern applications use these secrets today. So we've moved away from building what we used to call monoliths. So we'd have all this software where everything that software needed to run was internal. Now we are fortunate that we can rely on an architecture of microservices. So an easy one to talk about is Stripe, which is payment processing. Do you want to write your own credit card processing, or do you want to use a third-party service that just does that? And then we can extrapolate this to lots of things. Algolia is a search function. Okta is authentication. Mongo is a database, but we can have a managed database. So we can offshore all the things that isn't critical or unique in our application to third-party services, but all of these need to talk to each other. They authenticate using secrets typically. And each one of these is a potential entry point for an attacker to make their way into our infrastructure. Then once we have our application, we need to host it somewhere, we need to manage our source code, we need to test it. So all the tools that we use to do that also leverage secrets because they need to interact. And these are also entry points for attackers. Once we launch our application, marketing teams or engineering teams want to monitor it, see users, interact with different ticketing systems, more secrets, and then we haven't even talked about all the services that we've created. So this is just a really simple example just to show that really our applications are a collection of different services that talk to each other, leveraging secrets. So these secrets are highly, highly sensitive, and unfortunately, they end up everywhere. So one of the reports that we release in my company, GitGuardian, is the state of secret sprawl. So we do this every year, and we look at where we find these secrets out in public spaces. So one of the places we look is this website here, which is GitHub. Now there's about 100 million developers that use GitHub. If you're not familiar with it, this is the biggest kind of collection of source code online that there is. And what's interesting about GitHub is this is kind of like LinkedIn a little bit for developers, because this is where they put their portfolios, this is where they interact with open source tools. So you have to be interacting with GitHub if you're a developer today. It's very important. Some stats around about GitHub. There was 1 billion commits or contributions that were made to GitHub last year, just last year. So that's 1 billion times someone's written a segment of code and pushed that into GitHub in public places, just public places. So that's a huge amount of data. There's 85 million new public repositories. There was 94 million developers last year, but we've crossed over to 100 million. So what we decided to do at at GitGuardian, is we scanned the entirety of it. So we scanned all of those billion commits for 350 different types of secrets. So it was it's a mammoth task that requires huge amounts of computing processing, but we found a lot. So just last year, and just in public, and just on GitHub, we found 10 million secrets that were detected. This is about a 67% increase from the previous year. Now, because a lot of you are academics, it means you're allergic to bullshit. So I will, the 3 million of them were unique secrets, so 10 million total. Because we're referring to high entropy strings, it's very rare that it would be almost impossible that 2 of these would be identical. So 10 million total, 3 million unique. So how did this kind of progress over the previous years? So 3 million was when we first did it in 2020, and it's increasing. So why is it increasing? There's a few reasons for this that aren't because we're terrible. So one is that the amount of information on GitHub is increasing. So we're getting more data, so therefore more secrets. We're also getting better at detecting them, so that accounts for it. But we're also just leaking more secrets. So we used to leak secrets in source code, but now we have this thing called infrastructure as code. It's kind of like we manage our infrastructure with source code now. So that means that what might have been done internally with sysadmins is being codified and putting in repositories, and along with that, more secrets. So we're actually just leaking a lot more secrets than it is. And the kind of best comparison we have from previous years to now is that out of every 1,000 commits, we detect 5.5 secrets, right? So 11 secrets every 2,000 commits. That's a 50% increase from previous years. So that's showing that we're really increasing the amount of secrets that we're leaking, mostly because we're using them more. So we find specific detectors. So I'll break down what we actually found. So around about 24% was for databases and data storage. 20% was for cloud providers. Now, when we detect a couple of types of secrets, specific secrets and generic secrets. The specific secrets, we actually confirm that these are valid. So for example, this 20% of the cloud provider keys, so roughly 2 million total, we found, so that's just valid cloud provider keys. So we've checked with the cloud provider and said, hey, is this key valid? Can I do stuff with it? And they've said, yes, you can. What do you want to do? And then we've said nothing. And so that's huge amounts of data. Messaging systems, this is one of the favorites for attackers at the moment, because a lot of people seem to create, like for Slack or for Discord, like these bots that will message you when you get an email or something like that. And what attackers are using these for is internal phishing campaigns. So you find a hook that just posts to a random message, and you say, hey, you need to update your password, here's a link. So that's like a really way of breaking down a barrier of trust in a phishing campaign to get an elevated credential. So just for specific secrets, there's a really long line of like 350 types of secrets, but these are some of the main ones. Google API key is the #1. These can be varying levels of sensitivity. The GitHub access token is kind of funny. Where's that one? There. 3.5. So this is the access token for your private source code that you've put in your public source code. So it's kind of like, like you've sent an email and put your password in the subject line. This is kind of what's happening here. And with generic secrets, these are a lot harder we can't validate that these are actually real. There's definitely, we can be pretty confident in specific secrets that we don't have a lot of false positives. Here, it's very hard to tell how many. so they're not that big, but not too small. That same team will probably have about 4 AppSec engineers if they're lucky. When we first scan, we'll probably find 13,000 secrets. Again, this is the real number. 1,000 of them will be unique. This is huge. This is 1,000 secrets that are in an asset that is not well protected. So if we think about where we want to keep our passwords, where we want to keep our secrets, where we want to keep our passwords and where we want to keep our secrets, we want to have it in a vault, in a secrets manager, in a password manager, with access control, with lots of authentication, and we want to have fine-grained access logs of who's had access to it. So if we have a breach, we have all that information. Source code has none of that. So if something ends up in our source code, we have no way of ever being able to track where it ends up. So that's why this is a big problem. Now, these 4 AppSec engineers now have to try and find, rotate, communicate with the developers of what the secret does, issue new ones, and redeploy them 1,000 times without causing any outages. So it's really an impossible task. So that's why this is such a big problem. So typically what companies do is once they realize they have so many leaked secrets, they have to do something about them, so they typically just try not to look at the problem. This is what we find. So let's have a look at some a bit more of an elaborate attack path with a bit more consequences than the last one. So this one here, a credential for an employee of Uber was purchased on the dark web. Now this was a credential for a VPN, and that VPN had multi-factor authentication on it. So that should have been the end of the story. But they did multi-factor authentication spamming, just basically spamming the user with requests. That user eventually accepted that request, which granted the attackers access to their private network. The attackers did what all attackers do once they gain access to a private network, is they start enumerating all the data, scanning for more credentials, more access. They want to persist their access. Right now, their access is all hinged on this one credential that they purchased. So they want to try and find more access so that they can persist their attack. So they scanned it. There was a PowerShell script that they found in version control, in the source code, that had some credentials in it. So this credential was for Thycotic. It's a PAM system. So I'll just explain what this PowerShell script did. This was created by an admin who every time a new user, a new employee joined Uber, you have to create accounts for them on everything. So what they did is they automated that process by creating a PowerShell script. Hard-coded in that PowerShell script were the admin keys to basically the secrets manager and the password manager. So then the attackers were able to create accounts for themselves and persist access in every single one of Uber's services. So their AWS accounts, their Google Drives, their Slacks, all of their systems, the attackers were able to create accounts for themselves. So they took total ownership of everything in Uber. So this is a worst case scenario, and it all stemmed from a credential that was leaked, that was purchased on the dark web, and then basically bypassing it because there were other secrets in the network.
I can literally hear Bee Gees playing right now.
So just quickly, some other places that we find secrets as well. Docker is a place, there's this thing called a Docker image. It's basically like a very mini virtual machine. If I want to build an application, that application requires certain systems to run. So it's going to require this version of the database, this version of the operating system. Docker is a way of packaging everything that application needs to run in one area. So just a quick explainer. So basically, this is just applications. We can think of it like a .exe file plus in here. So we started scanning all the public Docker images on here to see how many of them had secrets. Things like Docker, things like mobile applications, people seem to think of them as these black boxes, that no one can gain access into them, that it's all totally jumbled up. But actually, there's just source code in there. It's not human readable, but we can still find secrets inside of it. So we found about 5%, almost 5% of Docker images contained at least one secret, which would give someone access into the infrastructure. So I just want to explain through another breach of why this is so important. So this one's a little bit technical, but mostly you just need to know it was really bad. So there is a company called CodeCov, and they did a very simple thing. When you test your application, when you test your source code, one of the things that you want to do is you want to see how much coverage of testing you have. CodeCov tested how much of your application was being tested. So it does a very specific job. It's set in the testing pipeline of an application, so it automatically would test. So what happened? How you installed CodeCov was through the Docker image that I was talking about on the previous slide. You would go to Docker, you would download their Docker image, and you would deploy CodeCov in your pipelines when you were running tools. Inside that, there was a hard-coded credential. That credential gave access to some more source code with read and write access. The attackers manipulated that source code. They injected one line of malicious code, which basically did one thing. When your application is being tested, it needs to build. So if you're connecting to a database, if you're connecting to a service, you need credentials to be able to build your application. So in the environment that CodeCov was running, there was lots of secrets. That one line of malicious code said, when CodeCov runs, I want you to dump all the environment variables, so all the passwords, all the secrets that you're using in your application, and I want you to send them to this remote address. Those attackers, CodeCov had 20,000 users in them. Big companies like HashiCorp, Twilio, Monday.com, Rapid7, all were using CodeCov, and the attacker was able to make it onto their internal infrastructure because they turned the CodeCov application malicious. So someone leaked a credential in a Docker image by just hard-coding it in there, forgetting that it was there. They were able to turn the application malicious, and then they had access to endless targets in a big supply chain attack. So that is one way where attackers can find these types of secrets and then really end up on lots of different infrastructure. So yeah, lots of ways. Hopefully we're not all getting too depressed. Okay, now let's talk about mobile applications. Because basically, there's secrets everywhere. The whole point of this is they're saying there's secrets everywhere. So mobile applications are generally saved in two different file formats. If it's an Android, it's saved as an APK, and it's put on the Play Store. If it's Apple, it's stored as an IPA, and it's put on the Apple Play Store. What you need to know is that a lot of developers think once they create this APK or this IPA, once they create their app, that it's locked down. It's somehow completely encrypted and you can't get anything out of it. These are just zip files. How you decompile an IPA is you change the extension to .zip and extract it with your zip extractor. They're just zip files. So I did an experiment to see how many Android applications had hard-coded secrets in them. So I just used this tool to download from the Play Store because you can't do it easily without a phone. I used this tool to decompile it, JDAX, and then I scanned it with GG Shield, which is a product that GitGuardian makes. I have a very quick demo. I will just skip through because I think it's going through, but I've downloaded the file, I'm decompiling it now, and I'm just running through for secrets. And so this is kind of on a random one. We have valid, this is a Google API. Oh, I'll wait till I get to the top. These are all the secrets that it's found. Generic passwords. So here we have a generic password. In here we have a Slack webhook that's valid. So this can be used for a phishing campaign or something. I have more generic passwords inside of here, and it goes on for quite a long time. I won't bore you with it. More Google API keys that are valid. And so this is just in a random APK that I found. So I did a webinar with some security researchers at Cyber News. We discussed some research that they did. So they took this on a much larger scale, and they scanned 50,000 APKs to try and find how many of them had hard-coded credentials, had passwords inside them on the Play Store. So they found, graphics are from this Cyber News that I'm sharing with permission, but they found about 55% of the applications on the Android Play Store had hard-coded secrets inside them. Now, this doesn't mean that 50% of them are completely pwnable, because some of them may be something like a Google Maps API key, or they could be a Firebase ID that, if it was configured correctly, wouldn't give access. But it's a huge amount of applications that are showing very poor practices in how they're handling their secrets and how they're handling their passwords. So what's the main amounts of secrets that they found? So Google storage buckets, they found about 17,000 of those out of the 50,000 applications that were scanned. So this is for data. So I'll give an example that uses buckets, which was from a banking app, but lots of sensitive information that gives lots of access. And this is all just because developers really don't understand how easily it is to reverse your applications once they've been compiled. So it's a big problem. The number one type of application that contained secrets was health and fitness apps. I wasn't particularly surprised by that, but there's a lot. And the best, which isn't on here, was the financial area. So now I want to show an example of how attackers were able to exploit this. So this exact example comes from a penetration tester called Jason Haddix, who shared this with me on my podcast of basically how he was able to get access to a lot of checks because of leaked secrets in the APK. So he had the APK, so the file he downloaded from the Play Store. This application had a feature where you could take image of a check and the bank would cache it. So by looking at this, he noticed that there was some insecure storage, so these checks were actually being stored locally on the phone insecurely. So that gave him an idea. He decompiled the application and found an S3 bucket, so just a database, where these pictures were being stored for. He had complete access through a hard-coded credential to that S3 bucket, and he had access to more than 10,000 images of unencrypted checks waiting to be cleared in this bank. So all this stems from the fact that there was a hard-coded credential in that APK, which basically ended up where Jason is a good guy, so this was on a penetration test. So in this case, the data was still secure, but it's massive vulnerability for the banks. So this proves that it's real, that there's a lot of really poor practices that creates lots of opportunities for attackers, essentially. Okay, so I get this question a lot when I talk about this. Like, how do you securely store secrets in a mobile application? How do you securely store secrets in the front end of a web application? And the secret is that you don't, right? You don't do this. You store all your secrets on the server side. And your application communicates with that server through authentication, so a user logging in, for example, and that's where it can retrieve its secrets from. I'm not talking about secrets that the application creates to encrypt stuff that can be stored in hardware on the phone. But this is basically the general advice for people, because I always end up having a lot of arguments and people kind of want to negotiate with me. They say, what if I split my APK, my API key? What if I split it up into different sections? And all these steps make it slightly more difficult for it. What if I obfuscate my code more? That makes it slightly more difficult for an attacker, but we will be able to tell that it's using an API. We'll be able to tell that it's using a password, and we will be able to find that through your application. So there's no secure way of storing it, and you can argue all you want. Some things that you can do, for example, Firebase is one that we find a lot of. You can restrict access to your API keys and things and your passwords so that only your application can access it, but you're relying on everything being configured perfectly. You're relying that everyone has to do their job completely perfectly, that there's no flaws in how this is being configured, and that hasn't created any vulnerabilities. So this is why, even if you try and argue with me that your APIs are actually safe because only your application can store them, you're adding a level of vulnerability that could be exploited. Some other things, like minifying your code. This is an example in Android. Like if you try and obfuscate your code, I really try and stress to developers, this makes it slightly harder. Slightly, only slightly harder. So it's really, I put these in here to try and prevent arguments of what I commonly get, but there's really no way to securely store secrets if you're going to use Docker, if you're going to store them in your mobile apps, if you're going to store them in your front end of your applications. Whatever you try and tell me, it's a poor practice. So how do we prevent leaking these secrets? So this is typically a lot on the developer side. So I know that this probably doesn't affect a lot of people, but the number one reason why we find hard-coded secrets is just that they're hard-coded into the source code. API key, password equals this. We never should do that. We should use environment variables. I can go into detail later on about what exactly those are. But basically, for developers, we should never hard-code secrets. We should never hard-code passwords. And ideally, developers should never have access to them through that. So always store our keys, our secrets on the back end. Centralize secrets in a centralized place, so ideally in a vault, like a secrets manager, a password manager, or in an environment variable file. And a lot of the secrets that we find are simply because files that should never be inside a Git repository or inside an APK or a mobile application make it there. And we can avoid that with simple things like adding a .gitignore file. So that's a file that will prevent certain file extensions or certain files from ending up inside with your repositories with the rest of your source code. Use vaults, secrets managers. Rotate your secrets regularly. This is one of the biggest points. And the reason why I say rotate your secrets regularly is for an obvious one is that if a secret leaks out in your source code, in an APK, in a mobile application, then if you're rotating them regularly, it won't be valid for long. However, there's another benefit for rotating secrets regularly, and I think this goes for all areas and passwords, is that if you're doing it regularly, you know how to do it. So if you do have a security incident, what a lot of people find is that a key gets leaked and no one has any idea what that key does. What is this password for? If you're rotating things regularly, then you have to have policies in place of what they're actually used for, how they're being used, and how to do that. So in the event of a data breach, that will help you a huge amount. And then the other area is restrict access to, of the keys. So there's a concept called zero trust, which is basically that just because I have a password, just because I have an API key, doesn't mean that I can use it however I want to use it. We should restrict access, so if that key is doing just one job, it's retrieving information from one specific thing, that's the only thing that that key has permission to do. And we can sign it with our applications, we can limit the IP addresses, so we can restrict everything down, so if I, as an attacker, find this key, I can't do anything about it. And so I just want to go back to my experiment really quickly. So I leaked this key a short time ago, and I just want to see. So here, maybe a little bit hard to see, these are all the requests and the IP addresses. We have the IP address from all the people that are using it. These are the tools that they're using. So Trufflehog is an open source tool to find secrets. This is using Python. So we can see that there is a lot of malicious actors in the last 5 minutes that have just tried to exploit this key. And this here is what they're trying to do. And generally what you'll see is that this is kind of the easiest call to make. So it's saying get caller identity. So they're connecting with my AWS account and saying, what is my, basically, is this valid? What's going to happen now is that whoever this threat actor is at the end of the day going to get a list of all the valid keys that they have, And then later on today, I'm going to see a whole bunch more different types of attacks for different things where they're going to be trying to elevate their privilege. So they're going to be trying to access different buckets, and they're going to work through a list of things to try and find out what this key does. And maybe they'll try and put some crypto mining on there. Maybe they'll try and do some other things. But that's generally what will happen. And then this key will end up being sold as part of a package of valid credentials on the dark web somewhere. And then later on, we'll get a whole bunch more requests. So yeah, don't leak your keys. So thank you. I hope that was interesting. I'll take questions.
I think Thomas was first.
So I really liked especially this experiment and how and to see actually how many attacks you get in such a short amount of time. So have you thought about this approach, like what if you, just like you did, leak a bunch of keys intentionally and use them as honeypots? So when someone tries to sign in the specific keys, then you immediately can blacklist those addresses and give them some kind of access so they don't notice that they are like blocked.
Yeah.
But they're like, they're gonna lose a lot of effort, like trying to do elevate their privileges or something, and they cannot.
Yeah, so the main purpose of what I did is I created what we call honey tokens. And the main idea of those is that I would put those AWS credentials in my infrastructure or even in my tools. And I should know that no one should ever try and connect with those keys. So I know that 100% of the attempts are malicious. So then I can put lots of things like I know someone's inside my Git repository, like a developer's account's been compromised, or my CI/CD pipeline is compromised. So yeah, we actually just there's companies that do this. Think's Canary is one. The tool that I used is from GitGuardian, but we've just rolled it out in beta, and we only do AWS keys at this point. But that is something we're looking at doing, extending this. Yeah.
It was in the left side menu. It was honey tokens beta, right?
Yeah. Honey tokens beta. Yeah, that's it. Yeah. But one of the cool things that we've done is we've got this. We did this little experiment. It's called SAS Sentinel, and we've leaked the honey keys in all of these different services. And the idea being is that none of them have been breached yet, but the idea being is that if our honey tokens get triggered, then we will know that these services have been compromised. So it hasn't happened yet, but it's a little experiment that we have going on, so hopefully that will happen.
I have a connecting question.
There are many questions here. Well, you get to pick my questions.
Jim? Yeah.
The format of the keys that you showed us looked like they were all like base 64. Do you handle other formats like UUIDs and things like that that are used as keys?
Yeah, in terms of like detection or honey tokens or?
In terms of detection.
In detection, yeah. So we have specific detectors and generic detectors. So we find 350 specific detectors. So for instance, an AWS key starts with the same 4 characters. It's a certain amount of fixed length, so we use regular expression to find it and then validate it. So we have 350 scripts, let's call them scripts, that will search for those specific detectors. We decode anything we can, so if it's wrapped in like base 64, we will decode it. And then when it comes to generic detectors, like a generic high entropy string, 90% of like a high entropy string is going to be something like a unique identifier that isn't necessarily sensitive. And it will create a huge amount of noise if we detect it on all of those. How we generally deal with that is that we capture them all, and then we run through post-validation to try and figure out if it's a secret or not. And we plug it back into a machine learning model to try and improve this. We think we're at about 70% true positive, but it's very hard to get accurate information on high precision and high recall without knowing, like 100%, because maybe it was valid, it's not anymore. There's lots of components, but we have lots of things, but it's difficult when it comes to generic things. Yes.
Yeah, thanks for the interesting talk. I was wondering regarding your advice to rotate the keys regularly from the user perspective, considering the developer as a user. Will this, what do you think, will this increase the probability that one of the keys will be leaked one day if you rotate that
all the time?
Yeah, so like, and this is an interesting argument from multiple sides. There's tools out there that rotate them automatically, and there's what we call just-in-time secrets too. This is the best practice. So there's a product called HashiCorp Vault, and what they'll do is it will create a secret for one use and then destroy it. These are great. Rotating secrets regularly, I don't like. You've got more touch points if you're doing it manually, and I guess that's the point. But if they do leak out, I mean, it's still much more secure practices. I'm sure there's a scenario where perhaps because of that extra touch point, it adds an extra risk, but I think that risk is kind of outweighed by the benefits of it, and areas like that. Because a similar argument that you get is that if you want to restrict the API keys to do the smallest possible job, you have to create more of them, which means that you have to handle more secrets, which means that there's more chance that a secret will leak out. But that's still more secure than having a master token that your whole life depends on. You know? Yeah. Yes?
So, not at all to argue, a genuine question and maybe a naive one because it's been exactly 10 years since I last developed for Android. So I completely agree with you that good practices are very easy for the most part, like 3-tier architecture, just put the database credentials further down the line and so on. But you mentioned Google Maps, and from what I remember, it's like a widget, it's awesome, you can embed it in your app, but then in the how-to it says like you need the API key, so how to not put it in the APK.
The APK. So you can still store those secrets and request them from the back end, and a lot of people don't. And a lot of people don't do this because they perceive that key is not that valid. But what we've also, like specifically with the Maps keys, is that there is no longer like a free tier of that. So there's so that still costs money. If I was developing anything that required Google Maps, I'm never going to pay for a Google Maps API key. There's so many available, like that, you know, like that I just can use. That is. You know, so things like that are difficult, but you can store all credentials as environment variables and request them. But because the Google Maps API key is basically handled more by the front-end team, that requires some communication with the back-end team. But yeah, it's like an interesting one because lots of people will say that that's not that sensitive. And you know, your life isn't going to fall apart if an attacker gets your API key for your maps. But I feel like just in terms of good coding practices, treat all API keys the exact same thing because it still can run up a bill.
So it's not that it all has to be server-side, but it's kind of okay if at least we download it in time, just in time.
Yeah.
Are there anyone that has to run because they have a plane or anything to catch? No? Okay, that's a good thing. I will, if that's okay with you, Hazel, I will suggest that we do 10-15 minutes so people can go outside and talk to Mackenzie and then Hazel can get ready for the very last official talk at PasswordsCon today. And thank you again, Mackenzie.
Thank you.
And now sound is on and video is on, and we have come to the last official talk of the day. And after the official talk, we are not going to run out immediately if you don't want to. Mats have asked to show the passwordless password manager for a couple of minutes afterwards. And I would also like to give you some information about Constitution Day tomorrow. And maybe we can set up a meetup this afternoon as well for talking more about passwords and pins and stuff like that. But now I am really happy to introduce Dr. Hazel Murray. She's been with PasswordsCon once before in Stockholm. Quantum multi-factor authentication. So as you can understand, I saved the best and the easiest topic for last.
Yeah.
Take it away.
Okay, so how many people know quantum mechanics? Ah, that's pretty good. Okay, so in order to explain our quantum multi-factor authentication algorithm, you're going to get a whistle-stop tour in quantum mechanics. So if you don't know quantum mechanics, it's never too late to learn. So yeah, this is my plan for the talk. I'm going to introduce quantum mechanics and then talk about like a simple authentication protocol using quantum computing, and then talk about our authentication protocol using quantum computing. So quantum computing started back in 1927 at a conference, and all these physicists got together and kind of put together, why are we getting all these anomalies in physics? And they came up with the field of quantum mechanics and the rules. But it wasn't until like 1980 that quantum computing came about. And the reason we're particularly interested in quantum computing in cryptography and security is because of these two algorithms. So the first one is Shor's algorithm, and it can basically easily factor large numbers. So that particularly affects RSA and elliptic curve cryptography. And it theoretically has the power to reduce RSA. It can guess like a 1024-bit key in just 4 hours. And the second algorithm is Grover's algorithm. It's not quite as effective. It's kind of basically a quick file search algorithm. And it can reduce the time to solve like a SHA-256 hash to 18,000 years. So we're not too worried about this one. But the Shor's algorithm is actually an issue. I mean, I say theoretically. Basically, we can theoretically do it, but we don't have like the quantum computers yet to actually do it. But like the estimate is maybe like 5 or 10 years time. So if you imagine all the cryptography that's using like RSA or elliptic curve cryptography, all of that's going to be vulnerable potentially in 5 to 10 years time. So there's probably you've heard about post-quantum cryptography, and that's looking at classical solutions that are going to work in a against quantum computing. But what we're interested in is quantum has these really cool properties. So what we want to know is whether we can build like new cryptographic protocols that are based on all these cool quantum properties. So what I'm going to do is I'm going to try and explain each one. Yeah. So the first thing is a qubit. So it's essentially the quantum equivalent of a bit. So a bit can be 0 or 1, but a qubit can basically be 0, 1, or any value on a sphere. So it can be like some proportion 0, some proportion 1, somewhere in between. And we say that it's in superposition if it's not 0, not 1, but somewhere in between. But the cool thing about a qubit that's in superposition is that it's in this kind of somewhere in between unknown value until we measure it. And when we measure it, it needs to decide whether it wants to say that it's 0 or 1. And that's actually what's meant by like a, this is just to say that the superposition is represented by a wave function. But that's actually what's meant by Schrödinger's cat. The kind of analogy that you have this cat, that it's in a box, you don't know whether it's dead or alive, it's not until you open the box that you know. That's the idea that it's in this superposition. We don't know what it is, it's not until we open and measure that it's either dead or alive. So I don't think it's a particularly good analogy, but that's what it's trying to kind of explain. So yeah, so when we measure, we find out like it has to, we say it collapses, so it collapses the wave function. So previously it was a wave function like some proportion 0, or like alpha proportion 0 and beta proportion 1. And when we measure it, it collapses, and it will go to 0 with the probability alpha squared, and it will go to 1 with a probability beta squared. So it's like probabilistic, basically. And, oh yeah, the other thing, oh yeah, that's Schrodinger's cat, yeah. The other thing I just wanted to mention is that when we measure, we say that we measure with a particular basis. All that means is if you imagine you're measuring something classically, you're either measuring like speed or distance or something like that. That's what we mean, is we have to measure with respect to something. Usually it's like horizontal or vertical.
I thought the cat meant the math was easy.
No. There's actually a thing about the cat that it was originally, Schrodinger was trying to explain that quantum mechanics can't possibly work because a cat can't possibly be dead or alive, but we've actually like changed it to be the explanation. But sorry. Okay, so then the next thing is entanglement. So this is kind of what Einstein described as like the spooky property of quantum mechanics. Sorry. So if we imagine we have two qubits, and they're both in superposition, so they're somewhere in between 0 and 1, we don't really know where. And we move one to the other, oh, and we entangle them. So that's the entanglement. And we move one to the other side of the world. You see my graphics? Yeah. Excuse me. And we measure one of them, and we get 1, then we know the other one's going to also be 1. And this is really weird because they're both based on a probability. They were seemingly kind of separate. There's no communication between them. But whatever I measure one to be, the other one will be the exact same thing. And that's like really powerful for like communications and stuff like that. So that's my whistle-stop tour of quantum mechanics. So congratulations, you passed. In terms of quantum authentication, there's 3 different types, generally. So we can use entanglement, we can use superposition, and we can use quantum communication complexity. And the one we use in our algorithm is quantum communication complexity. But the simple version that I'm going to show you is using entangled qubits. So the simple version is that we imagine we have a server. They create these entangled qubit pairs. And then they send one end of the pair to Bob, who wants to log in. Excuse me. All Bob does is he measures the qubit he receives. He gets like a 0 or 1 for each one of these, and then he sends back the code. And that's essentially his one-time pass. The good thing about this is that if you imagine an eavesdropper sitting in the middle, they're not able, like if they intercept these, if they measure them, it changes the state because it collapses the wave function, if you've mentioned. Thank you. So it will be obvious to Bob if someone's eavesdropped on the qubits as they're passed, which is quite a powerful property that we don't get with classical mechanics.
But can't they interfere in the communication?
They can. So this is why, a minute. So there's some flaws with this. So yeah, the last step is that the server measures their qubits and checks that it matches the code that Bob sends back. And if it does, they verify Bob. And there's some problems with this. So firstly, every time Bob wants to log into something, he's going to need a quantum communication channel, which isn't feasible at the moment anyway. The second thing, every time he wants to log in, the server's going to need to generate new qubits and send them to Bob, which again isn't, like, there's a lot of overhead there. And the third thing is that we still need a classical channel, and in particular, we need it to be a secured classical channel. So with the 2 other methods, you already need to have a secure classical channel, which means you already have like a shared key. So that's why it's not ideal. But yeah. Okay, so the authentication mechanism we focus on is based on this paper, which does like a proof of the quantum communication complexity theorem. And we show that it's possible to have it shows that it's possible to have a relationship between classical and quantum bits. And that a verifier can request measurements of the quantum bits, and they keep only the classical bits. Sorry. Just read that yourself for a minute. And basically, only holding the classical bits, they can verify that the user holds the relevant quantum bits. Okay. So the way this works is the server has these classical bit strings, like 4-bit strings. They convert them into 2 quantum registers, and our first paper actually showed how to do this conversion using like quantum logic gates. And they pass those to Alice. So the server keeps the classical strings, and Alice has the qubit registers. And the important thing is that Alice can't, from the qubit registers, she can't get the classical strings, but the server, they can basically generate new qubit registers if they want. So we are relying on a trusted server. Okay, so now if Alice wants to authenticate, we have the server over here with the classical strings, and Alice has the quantum token. So yeah, she stuns her token ID. The server selects some registers that should be measured. So, takes a selection and sends those to Alice. Alice then takes a subset. So there's actually she needs to take a particular fraction. She can't just decide to take all of them or none of them. So if they choose 6, Alice has to return 4 of them. So she agrees to measure a subset of the ones that the server has chosen. This just ensures that kind of neither the server nor Alice have full control over what things are chosen to measure. Then the server tells Alice what basis to measure each one with respect to. So depending on what basis we're measuring, we'll get a slightly different value. Alice performs these measurements and then sends the results back to the server. And the server basically has this equation that all they need to do is sub Alice's results into the equation. And if they satisfy the equation, then they know that Alice must have the real qubits, because there's no other way she could have got the results. And yeah, so then the server authenticates Alice. So there's kind of a few nice properties. So yeah, neither Alice nor the server has full control over what ones are chosen. Once something's measured, it can never be reused. But the nice thing is if you have a large enough token, you can use the token multiple times, because you'd just be measuring a fraction of your token, not the whole token. So you could just choose different registers and it will work again. So yeah, there is a trade-off though between the size of the token and how many uses it can have. The nice thing is that because the server is choosing how many registers or the first set of registers that should be measured, they actually have full control over how many are measured, which means that they're kind of determining how much security they want. So this is kind of how it can be built into risk-based authentication, is if it's a high risk, they can ask for lots of registers, and if it's a low risk, they can ask for just a few to kind of add a bit of validity. Oh yes, and one of the nice things is that, so all the things in purple are quantum and all the things in orange are classical. So there's actually no requirement for quantum communications, which means that so long as Alice holds a quantum token that can do quantum measurements, all the verifications are classical. So it makes it a lot easier. And also, the server, really importantly, only holds onto classical strings, because it would not be feasible for a server to hold quantum bits for every single one of their users. The scalability would just be impossible. I think that was all I wanted to mention. Oh yes, and then the key problem, in case you didn't know what the key problem with this wonderful scheme is that we don't have quantum memories. So in order for Alice to hold a token, she has to have some way of storing a quantum bit in memory that's entangled, because these are kind of made up of entangled and non-entangled bits. No, not entangled. These are in superpositions. So you need to hold a qubit in superposition. And I think at the moment... Yeah, well, at the moment, they can hold it for 2 seconds. So long as you can get your one-time code out to someone and back in 2 seconds, it's perfect. So, yeah.
Does that require liquid nitrogen or something as well?
Yeah, that shouldn't be an issue. Yeah. Silicon vacancy centers for all your users, and yeah, but yeah, it's a minor problem.
Movie on this, actually.
But the reason it's really important for us to look at this is because you've probably heard that like QKD is like becoming really popular. Like there's the EU is like building a whole quantum key distribution system throughout Europe. But a QKD doesn't have any built-in authentication. Like at the moment, it's all just classical. So if we could come up with a way to do like authentication on like through quantum computing or quantum communications, it could be like built in and attached to QKD. Like, do you know, you need to have the authentication linked to the key distribution. And at the moment, that's kind of an unsolved problem. So that's why it is useful for us to look at authentication, and hopefully in future, things like this will be more practical. Yeah, any questions? Yes.
Well,
oh,
yeah, thank you. And questions, and you can just point at whoever you want to listen to.
Okay, so partially you answered my question with the last sentence, because the presentation was mostly a quantum communication channel. So you have a laser, polarized light, you do the measurements. So and you can do like a Bell equality or CHSH equality to check if the shared secret is accurate and there are no eavesdroppers, right? But how can you implement this authentication mechanism without like having a quantum memory? So can't you just make it classical based on a quantum shared secret? So the security relies on the quantum level, so it cannot be broken. But then you just use like a traditional means of authentication. Like, how far is this from reality? Because this quantum memory is nowhere near practical levels.
Yeah, so if we do it like as like a real time, you know, like I can demo this basically with like I sent the qubits, we do the authentication immediately, and then I get the result. It's just the holding on to the token that's the issue at the moment. But I mean, these things are getting a huge amount of investment. So quantum computing is moving quite quickly. I don't think this in particular, like any solution that requires holding onto a quantum memory is quite a bit away. Like even only recently have they figured out how to do like quantum memories, but at room temperature. And that was huge progress. But like that's still not there yet. So I think probably we're more so looking at things like this, where it's kind of that instantaneous like measurements, and you get the kind of quantum properties like the BB84 protocol, which, yeah, you basically get the benefits of the quantum, but you never need to store the quantum. So as soon as the qubit arrives, you measure it, and you get the benefit of the eavesdropping protection, which you can't get in classical. So, yeah. Are there any other questions?
No more questions.
But you understood, right? Right?
I didn't. You don't have to count me into this.
Can I have another?
Yeah.
So what you mentioned is the entanglement-based approach.
Yeah.
Is the one that is used. So
I don't think any of these are used. Yeah. It's just more possible.
Right.
Yeah.
Okay, but why I'm asking is because you use an entanglement-based approach, like you create the entangled, it's usually on one side, because the ideal case is that you have something in the middle which sends the entangled bit, so that they kind of arrive together. But the reality is that you have it on one side, right? So you create you split the laser with a special crystal, and one light pulse like travels ahead, but one is immediately measured there on site. And that means that the photon then is not traveling in an entangled state, because as you do the measurement, the other particle immediately becomes the state that what you measured on site. So you cannot store this as a quantum information anymore, because it becomes classical.
Yeah, the problem is at the point that you do that, it becomes, it's susceptible to eavesdropping then.
Yeah.
Yeah, so you kind of lose the benefits of the quantum, other than like the random generation, which is kind of like useful as well, because you kind of have this intrinsic probability that kind of allows us to get nicer randomness-ish.
Then how do you like stall the measurement on your side? Because if you don't measure and you like circulate the entangled photon in, I don't know, what's it called, in a cable? Yeah, like I didn't, yeah. So as long as you don't measure, you are good. Like then the state is still in quantum.
Yeah, but it decoheres, so that's the issue. Yeah, that within 2 seconds it will decohere. So nothing wants to be quantum, it wants to be classical. Yeah. So it kind of, if you leave it in a superposition for too long, it will naturally want to become classical, and the superposition decoheres within 2 seconds, yeah.
I meant to say optical, okay. Right.
Yeah.
Okay, once again, thank you, Hazel.
Thanks.
And that means that our light